The observable universe is a truly fascinating concept that captures the imagination. Imagine, if you will, a vast expanse that stretches an astounding 93 billion light-years across. That is over 5.5 trillion miles, an extraordinary distance that challenges comprehension. It represents everything we can observe from our unique vantage point on Earth, bound by the cosmic horizon created by the finite speed of light. To understand the observable universe, we can start with the idea of light. Light, traveling at a speed of about 299,792 kilometers per second, defines the limits of our view. When we look at the night sky, we are peering back in time. The light from nearby stars may take only a few years to reach us, while light from the most distant galaxies we can see has been traveling for billions of years. This means when we observe distant galaxies, we are looking at them as they were in the past, revealing distant cosmic events that have shaped the universe. Now consider the enormity of the observable universe. Within this immense stretch, there are an estimated 2 trillion galaxies. Each of these galaxies contains billions, or even trillions, of stars, similar to our own Milky Way. To grasp this scale, think of a single grain of sand on a beach. With that perspective, each galaxy is just as numerous as grains of sand, emphasizing the astonishing vastness of the cosmos. One of the notable features within the observable universe is the cosmic microwave background radiation, a faint glow filling the universe. It is a remnant from the early moments after the Big Bang, providing a snapshot of the universe when it was just a mere fraction of a second old. Studying this radiation allows scientists to trace the evolution of the universe, contributing to our understanding of its origin, expansion, and eventual fate. Galaxies come in various shapes and sizes, and observing these can shed light on their histories. Spiral galaxies, like the Milky Way, are characterized by swirling arms of stars, gas, and dust. Elliptical galaxies appear more rounded and contain older stars, while irregular galaxies lack a distinct shape. Each type offers clues about the processes of formation and evolution that have occurred over billions of years. Superclusters represent some of the largest structures in the observable universe. These colossal formations contain groups of galaxies bound together by gravity. For instance, the Laniakea supercluster, where our Milky Way resides, encompasses thousands of galaxies and spans approximately 520 million light-years across. This interconnected web of galaxies highlights the dynamic nature of the universe, where cosmic structures are ever evolving over time. In addition to galaxies and superclusters, the observable universe also includes mysterious phenomena, such as black holes. These regions of space have gravitational pulls so strong that nothing, not even light, can escape them. The supermassive black hole at the center of the Milky Way, known as Sagittarius, a star, has a mass equivalent to about 4.1 million suns. Exploring black holes and their environments not only challenges our understanding of the laws of physics, but also opens up new avenues of research on the nature of space and time itself. Cosmic events, such as supernovae, are also within the realm of the observable universe. A supernova occurs when a massive star exhausts its nuclear fuel, leading to a spectacular explosion that can outshine entire galaxies for a brief period. The study of supernovae provides clues about the life cycles of stars and the intricate processes that govern stellar evolution. These cataclysmic events also play a crucial role in spreading elements across the universe, contributing to the formation of new stars, planets, and ultimately, life itself. Dark matter and dark energy are integral parts of the cosmic puzzle that compose about 95% of the universe. While regular matter, the kind that makes up stars, planets, and living organisms, accounts for only about 5%, the nature of dark matter and dark energy remains one of the biggest mysteries in cosmology. Dark matter acts as an unseen gravitational glue, influencing the motion of galaxies and the large-scale structure of the universe. Essentially, it binds galaxies together, creating a framework that governs the dynamics of cosmic evolution. Dark energy, on the other hand, is thought to drive the accelerated expansion of the universe, giving rise to questions about the ultimate fate of everything we observe. The observable universe is not static. It is a dynamic and ever-evolving expanse. The galaxies within it are moving, some racing away from each other due to the expansion of space itself. This movement, described by Hubble's law, can teach us about the history of the universe, including its initial singularity. By observing these cosmic phenomena, scientists gain insights into the forces that have shaped the cosmos and continue to influence its evolution. In this grand tapestry of existence, each star, each galaxy, and every phenomenon has its story to tell. The observable universe serves as a canvas painted with the light of billions of galaxies and cosmic events, inviting us to explore deeper into its mysteries, whether through powerful telescopes or by simply gazing at the night sky. It sparks curiosity, inviting inquiry into our place in this expansive universe. Each observation allows us to connect with something larger than ourselves, reminding us of the endless possibilities that exist way beyond our earthly realm. As we continue to explore and expand our understanding, the quest for knowledge will undoubtedly lead us to discover even more wonders that await in the vastness beyond. The universe is a vast and mysterious place, filled with wonders that intrigue scientists and curious minds alike. One of the most remarkable phenomena is often overlooked: the cosmic microwave background, or CMB for short. This faint glow fills the universe and carries with it secrets from a time long before most of us can imagine. To understand the significance of the CMB, we must journey back in time, nearly 13.8 billion years ago, to the very dawn of our universe. Imagine the universe in its infancy, a scorching, dense soup of particles and energy. At this point, the cosmos was not the star-filled expanse we see today. Instead, it was an almost incomprehensible swirl of energy, a place filled with potential and possibilities. As time passed, the universe began to cool and expand. As it did, particles started to combine, leading to the formation of simple atoms, mainly hydrogen and helium. This transformation paved the way for the universe we inhabit today. Just after this initial formation period, around 380,000 years after the Big Bang, an important event took place. The universe cooled down enough for those free-floating electrons and protons to come together to form neutral hydrogen atoms. This moment, known as recombination, marked a significant transition. Before recombination, the universe was an opaque plasma that prevented light from traveling freely. After this moment, light could finally escape, creating what we now see as the cosmic microwave background. The CMB is not just some random glow. It is the afterglow of the Big Bang itself, filled with information about the early universe. When scientists observe the CMB, they are essentially looking back in time, peering into the very beginnings of existence. This light is incredibly faint, a mere fraction of what we observe from the stars and galaxies. However, it permeates the universe and carries a wealth of information about its history. When the CMB was first detected in 1965 by astronomers Arno Penzias and Robert Wilson, it was a groundbreaking discovery. The faint microwave radiation they stumbled upon became a crucial piece of evidence supporting the Big Bang theory. What they found was a uniform glow that could be detected from all directions in space, suggesting that the universe was once in a hot, dense state. Delving deeper into this cosmic glow reveals fascinating details. The CMB is remarkably uniform, with slight fluctuations in temperature. These tiny variations represent the seeds of all the structure that would later form in the universe: galaxies, stars, and planets. By studying these temperature fluctuations, scientists can gather insights into the distribution of matter and the rate of cosmic expansion, helping us understand how the universe evolved over billions of years. The CMB also provides clues about the fundamental components of the universe. For instance, it helps astronomers determine the amount of dark matter and dark energy present in the cosmos. Dark matter, an invisible force that does not emit light, plays a crucial role in how galaxies form and how gravity affects the universe's structure. Dark energy, on the other hand, is the mysterious force driving the accelerated expansion of the universe. As we peer into the CMB with increasingly advanced technology, researchers utilize powerful telescopes and satellites, such as the Planck satellite launched by the European Space Agency. These instruments enable scientists to analyze the CMB with unprecedented precision, mapping its temperature variations and extracting vital information about the cosmos. The CMB serves as a cosmic background, a steady reference point against which many other observations can be compared. It is a treasure trove of data that continues to reveal the intricacies of our universe. Furthermore, the CMB is a reminder of the grand scale of the cosmos. It spans across billions of light years and represents a maximum distance we can observe. Beyond the CMB lies regions of the universe that are beyond our current capabilities to study. It encapsulates not just the history, but also the journey of the universe, from an extraordinarily hot and dense state to the complex web of galaxies and cosmic structures that we see today. In this sense, the cosmic microwave background is more than just ancient light. It is a link to our past, a connection to the moments that shaped everything we know. As we gaze upon the universe, we are reminded of the explosive beginnings that set the stage for the cosmic ballet of stars, galaxies, and planets that followed, a dance that continues to evolve with time. So, the next time you look up at the night sky, consider this faint glow that envelops the universe, whispering secrets of cosmic origins from billions of years ago. The CMB is a bridge across time, a beacon of history that anchors our understanding of the universe in the whirlwinds of stellar evolution and cosmic expansion. It invites us to remain curious and inquisitive about the mysteries that lie beyond, urging us to delve deeper into understanding our place in this vast, extraordinary universe. The multiverse theory is a fascinating concept that stretches the imagination and challenges our perceptions of reality. It suggests that the universe we inhabit might not be the only one, but rather just one of a vast array of universes that exist simultaneously. Imagine a boundless expanse filled with countless bubbles, each representing a different universe, varying in their own unique laws of physics, constants, and conditions. To understand the multiverse theory, let us first consider the fabric of the universe we are familiar with. Our universe is governed by fundamental forces and constants which dictate how everything operates, from the tiniest particles to the grandest cosmic structures. However, what if these rules could change? What if, in another universe, gravity was repulsive instead of attractive, or the speed of light was different? The multiverse theory proposes that these variations could exist in alternate realities alongside our own universe. There are several models within the multiverse framework, each offering a different perspective on how these alternate universes could manifest. One of the most prominent models is the cosmic inflation theory, which suggests that during the rapid expansion of the universe right after the Big Bang, different regions of space expanded at different rates. This could create pocket universes within the inflationary bubble, leading to an infinite number of universes, each with their own distinct physical properties. Another intriguing aspect of the multiverse theory comes from quantum mechanics. The interpretation known as the many worlds interpretation posits that every time a quantum event occurs, such as a particle being observed in a particular state, the universe splits into separate branches. Each possible outcome of that event exists in its own universe. This means that every decision you have ever made could create a divergent timeline, leading to an array of unique realities where alternate versions of yourself exist. Imagine a scenario where you chose a different career path or decided to move to another city. In one universe, you might be living your dream life, while in another, you may have taken a completely different route. Each of these possibilities unfolds into its own universe, creating an intricate tapestry of existence. The implications of the multiverse theory extend beyond mere speculation. They challenge our understanding of physics and the very nature of existence. For instance, if our universe is just one of many, what does that mean for our sense of belonging? Do we have a unique purpose in a multiverse filled with an infinite number of lives and possibilities? These thoughts lead to profound philosophical questions about identity, reality, and the nature of consciousness. Moreover, the multiverse theory opens doors to astonishing possibilities regarding extraterrestrial life. Imagine worlds where different forms of life could evolve under entirely different physical laws. In some universes, complex life could thrive in environments hostile by our standards. Other universes might not even allow for life as we know it, yet they could harbor creatures adapted to their unique laws of physics. The quest to understand the multiverse encapsulates humanity's desire to explore frontiers beyond our own understanding. While it remains a theoretical concept, the multiverse theory encourages scientists and thinkers alike to ponder beyond the limits of our known universe. This exploration drives advancements in physics, cosmology, and philosophy, sparking innovative ideas and fostering curiosity. As our technology continues to improve, the tools required to investigate these theories may become more refined. We are already observing phenomena like cosmic microwave background radiation, which provides clues about the early universe's conditions. Perhaps future observations could hint at the existence of other universes, or the dramatic events that unfolded during cosmic inflation. In literature and popular culture, the multiverse theme has sparked the imagination of writers and creators. From comic books to movies, we often encounter characters who traverse alternate realities, offering a creative lens through which to explore the implications of living in a multiverse. These stories serve not only as entertainment, but also as a means to engage deeper questions about who we are and what is possible. As we delve deeper into the science of the universe, theories like the multiverse invite us to look beyond the stars and reconsider our place in the cosmos. We may not yet have definitive proof of the multiverse, but the idea encourages us to explore, question, and ultimately embrace the vast, mysterious nature of existence. Each theory, each discovery, adds another layer to our understanding of reality, akin to peeling back the layers of an onion, revealing a complexity that is both exhilarating and humbling. In conclusion, the multiverse theory presents an enthralling possibility where our universe is intertwined among many others. It opens our minds to infinite scenarios, each unique in its own right, and pushes the boundaries of what we thought was possible. As we continue to explore the cosmos, the multiverse stands as a testament to the boundless potential of the human spirit and its insatiable quest for knowledge. The universe may be bigger and more intricate than we ever imagined, filled with mysteries waiting to be unveiled. So, as we gaze up at the night sky, let us ponder the vast multiverse, where every star could represent a gateway to an entirely different reality, brimming with infinite possibilities. The universe is a majestic expanse, filled with countless wonders, yet it also holds a myriad of mysteries that continue to puzzle scientists and enthusiasts alike. One of the most enigmatic substances that inhabit our cosmos is dark energy. This elusive form of energy accounts for a staggering 68% of the total energy content of the universe. Its effects can be observed in the way the cosmos is rapidly expanding, making it a fundamental aspect of modern astrophysics. To understand dark energy, let's first grasp the scale of the universe. Imagine standing on a vast plain, where each star you see is like a distant light from a tiny island in an endless ocean. As you gaze at the night sky, you might begin to appreciate that these islands are tirelessly moving away from each other. This movement is not merely an illusion. It is a reality influenced by dark energy. Unlike gravity, which pulls matter together, dark energy has a counteracting force, causing the expansion of the universe to accelerate. This counterintuitive behavior can be likened to blowing up a balloon. As air is pumped into the balloon, it expands outward. Likewise, dark energy causes galaxies to rush away from one another at an ever-increasing pace. To observe this phenomenon, scientists look at distant supernovae, explosions marking the death of stars in galaxies far beyond our own. What they discovered was astonishing. These supernovae were dimmer than expected. This dimness indicated that they were farther away than they would be if only gravity were at play. The conclusion was that there must be an unseen force compelling these galaxies to move apart more rapidly. Now, let's dive deeper into the nature of dark energy. While we know it exists and understand the role it plays in the universe's expansion, its essence, however, remains elusive. Scientists have proposed several theories to explain dark energy, each adding a layer of complexity to this grand mystery. One of the leading theories is known as the cosmological constant, introduced by Albert Einstein in his equations of general relativity. This constant represents a fixed energy density filling space homogeneously throughout the universe. Imagine a vast invisible ocean of energy that permeates all of the cosmos, subtly influencing its structure and expansion. Another intriguing hypothesis is the idea of a dynamic form of dark energy, changing over time. This concept suggests that dark energy could evolve and take on different properties as the universe ages. Chemical reactions in a laboratory may lead to different products over time, and similarly, dark energy might also change in behavior, influencing the fabric of the universe in unprecedented ways. This ever-shifting nature sparks curiosity and raises fundamental questions. Is dark energy truly a constant, or does it evolve? What if its influence morphs through eras of the universe's existence? Compelling observations have already ignited scientific curiosity. When assessing galaxies that are further away, we can observe them as they were billions of years ago. At that time, the universe's expansion was decelerating, suggesting that dark energy wasn't as dominant as it is today. As time progressed, the balance shifted, leading to the acceleration we witness now. This historical perspective offers a glimpse into the universe's evolving narrative, highlighting dark energy's critical role as a cosmic architect. Scientists are also looking toward future explorations. Future telescopes, equipped with cutting-edge technology, will aim to unveil further secrets of dark energy. They will probe deeper into the cosmos, gathering invaluable data on distant galaxies and supernovae. Insights gained from these investigations might shine a light on the nature of dark energy, perhaps illuminating how it intertwines with other forces of nature. As we explore the implications of dark energy, we are not only stepping into the realm of physics, but venturing into the philosophical. Dark energy raises profound questions about the universe's destiny. If dark energy continues to exert its influence, will it propel the universe towards an ever-expanding fate? The hypothetical scenarios range from eternal expansion, where galaxies drift further apart until all is cold and dark, to a more dramatic fate, like the Big Rip, where dark energy pulls everything apart, including atoms themselves. Whatever the ultimate fate of the universe may be, one thing is undeniable. Our quest to understand dark energy is tied to the very fabric of existence. It pushes the boundaries of astronomical knowledge and captivates the imagination. The intricate dance of galaxies, the dark voids of space, and the fundamental forces combine to create a narrative that invites us to ponder the grand design of the universe. As we look up at the cosmos, it invites a deeper reflection on our place within it. Dark energy, while shrouded in mystery, reminds us of the unknown possibilities that lie beyond our comprehension. It teaches us the value of inquiry and how curiosity fuels the journey of discovery. The universe is a vast expanse of questions waiting for answers, and the exploration of dark energy motivates us to look further into the mysteries of our existence. As we forge ahead into the depths of space and time, dark energy is a key that unlocks doors to infinite possibilities, inspiring us to expand our own horizons in this grand theater of the cosmos. Imagine holding a small teaspoon in your hand. Now, think about what it would be like if that tiny spoonful contained material from a neutron star. The sheer weight of that single teaspoon would be nearly inconceivable. It would come in at an astronomical weight, tipping the scales at more than billions of tons on Earth. To put this into perspective, a neutron star, which is the remnant of a supernova explosion, is one of the densest objects in the universe, second only to black holes. Neutron stars are fascinating celestial bodies that form when massive stars exhaust their nuclear fuel. As the core collapses under gravity's relentless pull, protons and electrons merge to create neutrons. This process leads to the formation of a star made almost entirely of these tightly packed neutrons, resulting in incredible densities that boggle the mind. The core of a neutron star is estimated to have a density exceeding that of an atomic nucleus, compressed into a sphere roughly 20 kilometers wide. To truly grasp the magnitude of a neutron star's density, consider this. If you could gather enough material from just one teaspoon would weigh as much as an entire mountain. This extraordinary density means that a sugar cube-sized amount of neutron star material would weigh approximately as much as all the cars on Earth combined. It is a mind-bending comparison that highlights how different the universe can be from our everyday experiences. Neutron stars have incredibly strong gravitational fields. The gravitational pull at their surface is so powerful that it distorts space and time. If someone were to stand on the surface of a neutron star, they would experience gravity about 2 billion times stronger than the force we feel on Earth. Only a fraction of the star's crushing mass is required to create such an immense gravitational well, distorting light and potentially even warping the very fabric of time in its vicinity. The intense gravitational pressures found in neutron stars led to remarkably strange phenomena. Pulsars, a type of neutron star, emit beams of electromagnetic radiation that sweep across the cosmos, much like a lighthouse. As the neutron star rotates, these beams can be detected from Earth as regular pulses, providing valuable insights into the universe. These pulsations can occur with remarkable precision, allowing scientists to study phenomena such as gravitational waves and the fundamentals of quantum physics. Understanding neutron stars also has implications beyond mere curiosity. They can serve as natural laboratories for studying matter under extreme conditions. The physics that governs neutron stars may help answer some of the universe's most profound questions. For instance, what happens to matter at incredibly high densities? How do these stars affect the surrounding environment? These questions drive research efforts to better understand the fundamental forces at play. In addition to gravitational forces, neutron stars also possess incredibly strong magnetic fields, millions to trillions of times stronger than Earth. This magnetic strength can influence their surrounding environment, leading to spectacular displays of energy. Sometimes, these magnetic fields accelerate charged particles around the star, producing high-energy radiation that rockets into space. This adds yet another level of complexity to understanding these extraordinary objects. Neutron stars can also merge with one another, creating events known as kilonovae. These catastrophic collisions result in the production of heavy elements, including gold and platinum, contributing to the cosmic factories that forge the elements essential for life. The energy released during such collisions can be observed across vast distances, offering astronomers a glimpse into the violent processes that shaped the universe as we know it. In summary, neutron stars are incredibly dense relics of supernova explosions, exemplifying the extremes of nature. Each teaspoon of their material places you in the realm of billions of tons, illustrating the immense forces and conditions that govern the cosmos. Their unique properties challenge our understanding of physics, gravitational forces, and the building blocks of matter. Whether through the pulsating beams of a pulsar or the cataclysmic merger of two neutron stars, their story is woven into the very fabric of the universe, revealing the beauty and mystery of the cosmos. The more we learn about these celestial phenomena, the more we uncover the fundamental truths about the universe itself. These stellar giants not only illuminate the night sky, but also our understanding of existence, matter, and the forces that bind us all. Imagine a region in the vastness of space, surrounded by an invisible boundary known as the event horizon. This unique feature defines the outer limit of a black hole, a region so powerful that once anything crosses this threshold, there is no turning back. It captivates the imagination and challenges our understanding of the universe. Picture the event horizon as a one-way door. Once you step through it, there is no way to return. Black holes themselves are remnants of massive stars that have exhausted their nuclear fuel. When a massive star collapses under its own gravity, it can create a black hole. The core compresses to a point of infinite density, known as a singularity, where the laws of physics, as we know them, cease to function in the way we expect. Surrounding this singularity is the event horizon, marking the boundary that separates the observable universe from the mystery beyond. Now, let us visualize the event horizon using a simple analogy. Imagine a whirlpool in a river. The water spins vigorously, pulling everything nearby toward its center. If you are floating close to its edge, you may still have a chance to paddle away to safety. However, if you are caught in the current and drawn closer, there comes a point where escape is impossible. This is similar to what happens at the event horizon of a black hole. The gravitational pull is so immense that nothing can withstand it once it crosses that line. One fascinating aspect of the event horizon relates to light itself. Light, the fastest traveler in the universe, cannot escape once it is captured by a black hole. This means that the event horizon is essentially a boundary of darkness, where information and matter can enter but never escape. For an outside observer, watching a star or a spaceship approach a black hole might seem like a dramatic event. As they near the event horizon, they would appear to slow down and fade away, never truly disappearing in a classical sense, but stretching and dimming as they approach infinity. The concept of the event horizon also invites intriguing questions. What happens to objects that cross this boundary? Many theories ponder the fate of matter swallowed by a black hole. Some suggest that it is crushed into the singularity, while others theorize that it may be transformed into a different state of existence. Yet, we still lack definitive answers, making the event horizon a tantalizing mystery in the cosmos. Notably, the event horizon is not a fixed object. It can change based on the mass of the black hole. If a new object, like a star or gas cloud, approaches a black hole and is drawn in, the event horizon expands. Conversely, if a black hole loses mass due to emissions like Hawking radiation, its event horizon contracts. This fluidity adds another layer of complexity to our understanding of these cosmic giants. As we consider the implications of the event horizon, we are also reminded of the profound nature of time and space near a black hole. The closer one gets to this boundary, the more gravitational time dilation comes into play. For someone nearing the event horizon, time appears to slow down relative to an observer far away. This means that while they might experience moments rushing by, an observer at a safe distance would see these moments stretching out in a bizarre but fascinating way. The concept of black holes and their event horizons has inspired countless stories, scientific exploration, and imagery throughout our history. In popular culture, black holes often embody the unknown. Movies and literature have depicted them as gateways to other dimensions or as cosmic predators. While these interpretations may be exaggerated, they reflect our deep curiosity and desire to understand the universe's mysteries. In conclusion, the event horizon of a black hole remains one of the most enigmatic and captivating features of our universe. It represents a boundary that challenges our notions of reality, inviting ongoing exploration and scientific inquiry. This boundary between the known and the unknown continues to spark our imagination, revealing the incredible complexity of the cosmos that lies just beyond our reach. As we delve into the mysteries of space, the event horizon will forever remain a symbol of the profound questions we still seek to answer about the nature of existence and the universe we inhabit. Pulsars are one of the most fascinating phenomena in the universe. Imagine being in a vast ocean, surrounded by darkness, with only the occasional beam of light piercing through. This is the cosmic role of pulsars, rapidly spinning neutron stars that act like celestial lighthouses, guiding our understanding of the cosmos. A pulsar is formed when a massive star exhausts its nuclear fuel and undergoes a supernova explosion. The core that remains after this explosion collapses into a neutron star, an incredibly dense object made mostly of neutrons. To put this into perspective, a sugar cube-sized amount of neutron star material would weigh as much as an entire mountain on Earth. These neutron stars are not just dense, they are also incredibly fast spinning. Some pulsars rotate hundreds of times per second. As they spin, they emit beams of radiation from their magnetic poles. Due to the orientation of these beams, they sweep across space in a manner similar to how a lighthouse projects its light over the ocean. When the beam of radiation points towards Earth, we detect a pulse of light and radiation. This is why they are called pulsars, as we receive a pulse of energy at regular intervals. The study of pulsars has opened up new avenues in astrophysics. For example, scientists have discovered over 2,000 pulsars in our galaxy, the Milky Way. Each of these pulsars has its own unique rhythm, emitting regular pulses that can be measured with incredible precision. This regularity allows astronomers to use pulsars as cosmic clocks. One of the most significant and exciting aspects of pulsars is their potential for deep space navigation. Just like ships at sea use lighthouses to navigate, spacecraft could use pulsars as reference points to calculate their position in the vast expanse of space. Because pulsars are distributed throughout the galaxy and have highly stable rotation rates, they could provide reliable markers for distance and direction, enabling more precise space travel in the future. A fascinating discovery was made with a type of pulsar known as a millisecond pulsar. These pulsars spin extremely fast, completing a rotation in just a few milliseconds. This incredible speed is thought to result from the accretion of material from a companion star in a binary system, essentially stripping material away and increasing the pulsar's rotation rate. These objects have helped astronomers gain insights into the conditions found in extreme gravitational environments. Moreover, pulsars can also be utilized to test theories of gravity. In particular, the behavior of binary pulsars can be studied to understand general relativity. For instance, researchers have observed how the gravitational waves generated by two orbiting neutron stars can affect their surroundings and how these ripples travel through space. By measuring the decay of their orbits, scientists have been able to confirm predictions made by Einstein's theory. Pulsars also play a significant role in exploring the matter under extreme conditions. The environments surrounding pulsars have high magnetic fields and immense pressures, making them unique laboratories for studying matter in ways that are impossible to replicate on Earth. Understanding these environments helps physicists learn more about fundamental forces and how matter behaves in extreme conditions. The phenomenon of pulsars extends beyond our Milky Way galaxy. Pulsars have been discovered in other galaxies as well. The study of these distant pulsars can provide insights into galactic evolution and the behavior of stars within those regions. Each pulsar serves as a beacon that carries information about the history of its galaxy, shedding light on processes that occurred eons ago. The use of pulsars as timing devices is also an exciting development in the field of gravitational wave astronomy. Researchers are now exploring a technique known as pulsar timing arrays. By observing an array of pulsars across the sky, scientists can potentially measure gravitational waves produced by distant supermassive black holes merging. This could lead to groundbreaking discoveries, giving us a clearer picture of massive cosmic events. As we continue to study these cosmic lighthouses, we uncover more about the universe's structure, behavior, and mysteries. Pulsars challenge our understanding of physics and push the boundaries of what we thought we knew about stellar objects. Each new pulsar discovery adds another piece to the cosmic puzzle, allowing us to explore the intricate dance of matter and energy in the universe. In conclusion, pulsars are extraordinary celestial objects that not only captivate our imagination, but also serve as essential tools for understanding the universe. They bridge the gap between the known and the unknown, lighting the way for future discoveries in astrophysics. By studying the rhythmic pulses of these neutron stars, we gain deeper insights into the nature of space, time, and gravity, making them crucial for unlocking some of the universe's most profound secrets. In the vast expanse of the universe, there lies a tiny patch of sky that, at first glance, appears deceptively unremarkable. This patch is situated in the constellation Ursa Major, not far from the Big Dipper. It is known as the Hubble Deep Field, a monumental photograph that was taken by the Hubble Space Telescope. This remarkable piece of celestial photography has opened a window into the past, presenting us with a breathtaking tapestry of galaxies, each with its own unique story. The Hubble Space Telescope, launched into low Earth orbit in 1990, was designed to capture images of the universe free from the blurring effects of Earth's atmosphere. With its powerful instruments, Hubble has allowed astronomers to peer deeper into the cosmos than ever before. In December 1995, a team of scientists decided to focus Hubble's powerful lens on a seemingly empty area of the sky, selecting a region that measured just a fraction of the size of the full moon. This bold decision culminated in one of the most astonishing discoveries in the history of astronomy. What they found was astounding. Over the course of 10 consecutive days, Hubble collected light from this small region, revealing a vast multitude of distant galaxies. The resulting image displayed over 3,000 galaxies, some of which are among the oldest and farthest known to humanity. The Hubble Deep Field is not just an image. It is a sight filled with mysteries and wonders that stretch back billions of years in time. To truly grasp the significance of what we are looking at, it is essential to understand the immense scale of the universe. Galaxies come in various shapes and sizes, with some appearing spiraled like our own Milky Way, while others look elliptical or even irregular. The Hubble Deep Field showcases different types of galaxies in an array of colors, reflecting their differing distances from Earth and the stages of their evolution. Each point of light represents a galaxy, brimming with stars, planets, and potentially even life. One fascinating aspect of the Hubble Deep Field is that the light we see today has traveled for billions of years to reach our eyes. Some of the light captured by Hubble was emitted when the universe was still a very young place, just a few billion years after the Big Bang. This means that when we look at the image, we are not just seeing galaxies as they are now, but as they were in the distant past. It is as if we are peering back in time, witnessing the universe's early formations and its evolutionary journey. Not only does the Hubble Deep Field tell a story of time, but it also reveals the complexity of the universe. Among the thousands of galaxies, astronomers have detected signs of various cosmic phenomena. Some galaxies are busy forming new stars, while others appear to be interacting with or merging with neighboring galaxies. These interactions are fundamental to our understanding of galaxy formation and evolution. The Hubble Deep Field has also inspired further explorations of the universe. The success of this initial field has led to follow-up observations that delve even deeper into the cosmos. Hubble has conducted numerous deep field surveys, including the Hubble Ultra Deep Field and the Hubble Extreme Deep Field, all of which continue to expand our understanding of the universe. The implications of the Hubble Deep Field extend beyond the scientific realm. It serves as a humbling reminder of our place in the universe. Each galaxy, captured in that tiny slice of the sky, represents the potential for other worlds, stars, and civilizations. It invites us to ponder questions about existence, the nature of life, and our connection to the cosmos. Are we alone? Or are there other beings gazing up at their own night skies, contemplating the same mysteries? The legacy of the Hubble Deep Field continues to resonate within the scientific community and beyond. It has changed the way we approach astronomy and pushed the boundaries of what we believe to be true about our universe. As technology advances and telescopes like the James Webb Space Telescope come online, we are embarking on new adventures that will further illuminate the dark and distant corners of space. The Hubble Deep Field stands as a testament to human curiosity and ingenuity. It reminds us that the universe is vast and full of surprises, waiting to be uncovered. As we gaze upon that tiny patch of sky, we cannot help but feel awe at the enormity of what lies beyond our own world, compelling us to explore further and dream bigger. This extraordinary image encapsulates not just a moment in time, but a paradigm shift in our understanding of existence itself, motivating generations of stargazers, scientists, and dreamers alike to look to the stars and wonder about what lies beyond. In the vast expanse of the universe, there exist enormous structures known as galactic superclusters. These colossal formations are not just random collections of galaxies. They represent some of the grandest architectural designs of cosmic nature. To understand these massive structures, let us delve into their unique characteristics and the extraordinary role they play in the cosmic tapestry. A galactic supercluster is essentially a group of galaxy clusters and groups that are gravitationally bound together. Imagine standing on a beach and looking out at a horizon dotted with tiny islands. Each island represents a cluster of galaxies, while the entire shoreline encompasses a supercluster. One of the most famous examples of a galactic supercluster is the Virgo supercluster, which encompasses our own local group of galaxies, including the Milky Way. Galactic superclusters can span hundreds of millions of light-years across, showcasing an astonishing variety of galaxy types. These structures are home to a myriad of galaxies, from elegantly spiraled types like our Milky Way to irregular galaxies that appear as distorted shapes. Each galaxy within a supercluster may host billions of stars, planets, and potentially even life, forming a diverse cosmic community. The formation of galactic superclusters is a fascinating process that reflects the history of the universe itself. Initially, the universe was a dense and hot soup of particles. As it expanded and cooled, matter began to coalesce under the influence of gravity, forming the first galaxies. Over billions of years, these galaxies began to cluster together, driven by their gravitational attraction, ultimately leading to the formation of superclusters. This clustering is not random. It is a reflection of the distribution of dark matter and the energy that shapes the universe. Interestingly, galactic superclusters are interconnected through vast cosmic filaments of galaxy clusters and dark matter, forming a web-like structure known as the cosmic web. This enormous framework stretches across the universe, linking superclusters together in a grand, interconnected network. It can be likened to a spider's web, where the superclusters are the points of intersection, and the strands are the filaments of matter that bind them. Within these superclusters, there are regions of higher density, where galaxies are packed closely together, as well as voids, which are vast expanses with very few galaxies. This uneven distribution of galaxies leads to a rich cosmic landscape that varies dramatically from one region to another. Such variations fuel our curiosity about the universe's origins and its ultimate fate. Galactic superclusters are also key to understanding the expansion of the universe. Astronomers study the movement of galaxies within these superclusters to gain insights into cosmic phenomena. By observing the redshift of light emitted from galaxies, scientists can determine how fast they are moving away from us. This movement is influenced by the universe's expansion and provides a window into understanding dark energy, the mysterious force driving that expansion. One of the most intriguing aspects of superclusters is their impact on cosmic evolution. The interactions between galaxies within a supercluster can lead to galaxy mergers, a process where two galaxies collide and combine into a single, larger galaxy. These mergers can trigger star formation, resulting in spectacular bursts of activity that illuminate the night sky. The remnants of such events shape the future of everything involved, creating new galactic structures that may roam the universe for billions of years. As we look to the cosmos, it becomes evident that galaxies don't exist in isolation. They are part of vast communities that influence one another through gravity, radiation, and interaction. Superclusters serve as monumental laboratories for astronomers and physicists, offering a rich field for research and discovery. Scientists are continually analyzing data from various telescopes and space missions to gather more information about these enormous structures and their role in the larger cosmic picture. Exploring galactic superclusters not only reveals the grand architecture of the universe, but poses deep questions about our place in it. How intertwined are our galactic neighborhoods, and what stories do they tell about the genesis of the cosmos? With every new discovery, we gain a richer understanding of the complexities and wonders that encompass our universe. The next time you gaze up at the night sky, consider that the twinkling stars belong to galaxies that are part of much larger structures, like cosmic superclusters. Each speck of light represents not just a single star, but an entire universe of potential interconnected by gravitational forces that stretch across unimaginable distances. This realization adds layers to our appreciation of the cosmos, transforming the simple act of stargazing into a profound journey through time and space. As we continue to unravel the mysteries of the galactic superclusters, we venture deeper into the fundamental questions of existence. Each discovery brings us closer to understanding the universe's origins, its mechanics, and ultimately, our own history in the magnificent saga of existence. Time is one of the most fascinating concepts in the universe, one that we often take for granted. We measure our days by the ticking of clocks, our years by the cycle of seasons. However, in the realm of physics, time is not just a constant flow, unaffected by external influences. In fact, the nature of time becomes particularly intriguing when we delve into the effects of gravity and speed, a phenomenon known as time dilation. Imagine you are standing on the surface of a planet, feeling the pull of gravity clinging to your feet. This pull is a manifestation of the planet's mass. According to Einstein's theory of relativity, this mass influences not just the space around it, but also the flow of time itself. The stronger the gravitational force, the slower time moves. To illustrate this, let's consider a scenario involving two clocks, one that stays on the surface of a massive planet, and another that is sent far away into deep space. If we were to observe these two clocks, we would find something astonishing. The clock that remained on the planet would tick noticeably slower compared to the one floating in the quiet expanse of space. This isn't merely a trick of perception. It's a fundamental characteristic of how time interacts with gravity. The greater the mass of the object creating the gravitational field, the more pronounced this effect becomes. For example, near a black hole, where gravity is incredibly strong, the effect of time dilation is extreme. To an outside observer, someone nearing a black hole would appear to move in slow motion, as their clock lags far behind those of distant observers. But time dilation also occurs at high speeds. Think about traveling in a spacecraft that approaches the speed of light, which is approximately 300,000 kilometers per second. According to special relativity, as you accelerate closer to this incredible speed, time will begin to behave differently for you than for those who remain stationary on Earth. If you could somehow maintain that high speed for a journey through space, you would experience a much shorter duration of time compared to people back on Earth. This means that if you embarked on a round-trip journey at near light speed and returned after what felt like just a few years for you, many more years could have passed on our home planet. This concept can seem abstract, but let's break it down with a practical example. Imagine a twin scenario, similar to the famous twin paradox. One twin stays on Earth, leading a normal life, while the other is launched on a high-speed space mission. As the traveling twin journeys through the cosmos at near light speed, they experience less time due to the effects of velocity on time. When the journey concludes and this twin returns, they might find that their sibling has aged significantly more than they have. These principles challenge our conventional understanding of time as a uniform experience. Instead, it becomes evident that time is a commodity that is versatile, affected dramatically by the influence of both speed and gravity. Not only does this offer an incredible glimpse into the workings of our universe, but it also raises thought-provoking questions about reality. If we could harness the power of speed and gravity, what adventures might lie ahead? One fascinating application of these theories is in the realm of modern technology. The Global Positioning System, or GPS, relies on a network of satellites orbiting the Earth. These satellites experience both gravitational time dilation, because they are further away from Earth's gravitational pull, and relativistic effects due to their high orbital speeds. Engineers must account for these discrepancies, adjusting the satellite clocks to maintain their accuracy on Earth's surface. Without these adjustments, GPS readings would accumulate errors of several kilometers each day. Understanding time dilation encourages us to look beyond our everyday experiences and appreciate the complexities of the universe. Whether it's the subtle pull of a massive planet or the exhilarating rush of speed, these phenomena serve as a gateway to contemplating concepts that redefine our perceptions of existence. As we ponder the wonders of time and its relationship with the universe, it becomes clear that the exploration of such profound ideas can inspire a sense of curiosity and awe. While our clocks tick on, the very fabric of time eludes certainty, woven intricately into the tapestry of the cosmos. We are reminded that there is much more than meets the eye, and that time, in its elusive nature, dances to the rhythm of gravity and motion. So, the next time you look at the clock, consider the extraordinary world of time dilation swirling just beyond your perception. It's a testament to the beauty of science, where abstract theories lead to mind-bending realities, reshaping how we understand not only time, but also the very essence of our place in the universe. The great adventure of knowledge continues, revealing layers of mystery that beckon us to explore further into the depths of space and time. Planck time and Planck length represent incredibly small scales within the realm of physics, serving as crucial concepts in our understanding of the universe at its most fundamental level. To grasp these ideas, it is essential to first comprehend what they signify and how they challenge our perceptions of space and time. Planck length is defined as the distance light travels in a vacuum in 1 unit of Planck time. This minuscule distance is approximately 1.610 to the power of -35 meters. To put this into perspective, envision a proton. The Planck length is about 20 orders of magnitude smaller than the size of a proton, making it an unfathomably tiny measurement. In essence, it forms a boundary beneath which current physical theories cease to operate effectively. Now, let's explore Planck time. Planck time is defined as the time it takes for light to traverse the distance of 1 Planck length. This measurement is defined to be about 5.391 x 10 to the power of -44 seconds. To understand how short this duration is, consider this. If 1 second were scaled to the lifetime of our universe, the entire span of the universe's existence would last only a second when compared to a Planck time. Want to see? Both Planck time and Planck length emerge from the synthesis of fundamental constants: the speed of light in a vacuum, the gravitational constant, and Planck's constant. These constants form the backbone of many core equations in physics, underlining the significance of Planck units. By simple mathematical derivation, one can see that these Planck units emerge not from arbitrary definitions, but from the very nature of the laws governing the universe. In the world we observe, we experience reality at scales that are vastly larger than Planck units. Our human experience tends to be confined to the macroscopic domain, where measurements are influenced by gravity, electromagnetism, and other forces that seem to govern everyday life. However, at the scales defined by Planck time and Planck length, it becomes apparent that traditional concepts of length and duration lose their meaning. This intriguing realm invites a host of questions surrounding the nature of reality itself. The implications of these minuscule measurements extend far into theoretical physics, especially in fields like quantum gravity and string theory. Here, physicists speculate on the structure of spacetime itself, suggesting it may be quantized at the Planck scale. In this context, spacetime could behave more like a series of discrete units rather than a smooth continuum as currently understood. A fascinating visualization is to think of the fabric of spacetime as akin to a woven tapestry. If we zoom in infinitely on a single thread of this tapestry, we might begin to encounter the granularity that Planck length suggests. Each thread could represent a fundamental unit of distance, and the knots that hold the threads together could symbolize the forces of nature acting at these incredible scales. Additionally, exploring beyond the Planck scale opens doors to novel theories, attempting to unite the principles of quantum mechanics with general relativity. In this endeavor, researchers grapple with concepts such as the very beginning of the universe, black holes, and singularities. These areas are rife with enigmatic behaviors that remain unresolved under our current paradigms. The uniqueness of Planck time and length also provides insight into some of the universe's most bewildering phenomena. For instance, when contemplating the Big Bang, the initial conditions of the universe may have existed at scales where the classical laws of physics simply do not apply. Here, the significance of Planck units becomes crucial, as they provide a framework for thinking about what before and during might have meant in such primordial moments. As our understanding of the universe evolves, the concepts of Planck time and length continue to challenge and expand our comprehension of reality. Their implications resonate through the fields of cosmology and theoretical physics, where they push the boundaries of what we know and what we have yet to discover. Investigating these tiny scales may lead not just to a greater understanding of space-time, but also to untangling the mysteries of gravitational waves, quantum entanglement, and even the fabric of reality itself. When pondering the enormity of the universe, it is humbling to recognize that, at the tiniest scales, the laws of nature take on a vastly different form. The pursuit to understand Planck time and length is an ongoing journey into the unknown, one that promises to deepen our understanding, not only of the universe, but of our very existence within it. Each tiny unit reminds us that the universe is a tapestry woven together by forces and phenomena far beyond everyday experience. It is a reminder that in the depths of the cosmos, there is always more to learn, more to uncover, and endless mysteries waiting just beyond the veil of our current understanding. Hypernova explosions are among the most powerful and spectacular events in the universe. These stellar phenomena occur when massive stars, typically more than 30 times the mass of our Sun, reach the end of their life cycle. Unlike typical supernovae, which are already powerful displays of cosmic energy, hypernovas release a colossal amount of energy, making them some of the brightest events known in astrophysics. The conditions that lead to a hypernova explosion are complex. As a massive star exhausts its nuclear fuel, the core begins to collapse under the force of gravity. This collapse happens incredibly quickly, within a matter of seconds. When the core reaches critical density, it triggers a violent explosion that ejects the outer layers of the star at astonishing speeds. Imagine the energy released being equivalent to that produced by our Sun over its entire lifetime, all unleashed in a matter of moments. Hypernovas also play a crucial role in the enrichment of the universe. During these explosions, elements forged in the star's interior, such as carbon, oxygen, and nitrogen, are released into space. This outflow of heavy elements contributes to the formation of new stars and planets, seeding the cosmos with the ingredients needed for life as we know it. The debris from these colossal blasts can create nebulae, the colorful clouds of gas and dust that serve as nurseries for new stars. One particularly fascinating aspect of hypernovas is their association with gamma-ray bursts, which are among the most energetic events in the universe. When a hypernova occurs, it is possible for it to emit beams of gamma rays directed along the rotation axis of the star. If these beams are aimed at Earth, they can be detected across vast distances, appearing as brief and intense flashes of gamma radiation. These bursts can outshine entire galaxies, making them detectable even billions of light-years away. The energy output of a hypernova can be several times greater than that of a typical supernova. To put this into perspective, while a supernova might shine with the luminosity of the entire Milky Way galaxy for several weeks, a hypernova can illuminate its surroundings with the brightness of hundreds of billions of suns for a much shorter duration, typically lasting only days to weeks. This brief but intense luminosity can create waves of fascinating phenomena in the surrounding space. Astronomers utilize hypernovas to study the universe and even to probe the fundamental nature of cosmic physics. Observations of these spectacular explosions can provide valuable insights into the life cycles of massive stars and the processes that govern their deaths. They serve as cosmic laboratories, allowing scientists to test theories about the fundamental forces that shape the behavior of matter and energy on a grand scale. Hypernovas are rare events which only occur a few times in a galaxy over the course of 1,000,000 years. Their rarity is part of what makes them so captivating for astronomers and enthusiasts alike. Only a handful of hypernovas have been observed since the advent of modern astronomy, with notable examples such as C1998 BW, which erupted in conjunction with the gamma-ray burst GRB 980,425. The identification of such hypernovas has sparked intense interest in unraveling the mysteries surrounding the life and death of massive stars. The cosmic scale and significance of hypernovae extend beyond just their impressive display of light and energy. Understanding these phenomena can shed light on the formation of black holes and neutron stars. The core that remains after the explosion can collapse into a black hole, a region of space where gravity is so strong that nothing, not even light, can escape it. On the other hand, if the remaining core is not massive enough, it might stabilize into a neutron star, an incredibly dense remnant composed almost entirely of neutrons. Exploring hypernova explosions not only enhances our understanding of stellar evolution, but also gives us a glimpse into the cosmic future. The energy and materials expelled during a hypernova contribute to the cosmic ecosystem, influencing star formation and the evolution of galaxies over time. It's a reminder that the universe is not static, but is an ever-changing tapestry of creation and destruction, where each explosion serves as a catalyst for new beginnings. As we continue to observe the universe and enhance our technological capabilities, astronomers are excited about the potential to discover more about hypernovae and their impact on the cosmos. Each hypernova we study opens up questions about the nature of the universe, inviting us to ponder the complexities of stellar life cycles, the interstellar medium, and the formation of galaxies. In this grand cosmic dance, hypernova explosions stand out as radiant markers of both destruction and creation, illuminating our understanding of the universe in unimaginable ways. The awe-inspiring power of these explosions reminds us of the dynamic nature of the universe and the intricate processes that govern it, beckoning researchers and enthusiasts alike to delve deeper into the mysterious realms of space. In the vast cosmos, there exists a fascinating phenomenon known as the Great Attractor, a gravitational anomaly that has intrigued astronomers and scientists for decades. Imagine a colossal entity, a force so powerful that it influences the motion of entire galaxies, including our very own Milky Way. This mysterious region lies somewhere in the direction of the Centaurus and Hydra constellations, and though it holds immense gravity, much about it remains hidden from our direct observation. To understand the Great Attractor, one must visualize the structure of our universe. Galaxies are not static. They move through the cosmic tapestry, influenced by the gravitational pull of large masses. What sets the Great Attractor apart is its scale and the enigma it presents. It serves as a gravitational focal point, and its influence extends over a vast area of space, pulling galaxies towards it over immense distances. The Great Attractor is found within a supercluster of galaxies known as the Laniakea Supercluster, which includes around 100,000 galaxies, spanning about 520 million light-years across. Our own Milky Way is located on the outskirts of this enormous structure. As we journey through space, we find ourselves in a gravitational dance, swaying toward this immense force, an invisible hand guiding our motion. What exactly is the Great Attractor? Researchers believe it is likely a region of high density, packed with galaxies, dark matter, and possibly clusters of galaxies that exert a powerful gravitational pull. However, observing this area is quite challenging. It lies behind the Milky Way's dense disk, filled with stars and cosmic dust that obscures our view. This obstruction prevents us from seeing the Great Attractor directly, leaving us to infer its presence through the movement of galaxies. Astronomers utilize the redshift method to study the motion of galaxies, observing the light emitted from them. When a galaxy moves away from us, its light shifts to the red end of the spectrum. By analyzing these shifts, scientists can map the velocities and trajectories of galaxies. The data collected indicates that numerous galaxies are heading in the direction of the Great Attractor, suggesting a substantial gravitational influence at play. The concept of gravitational attraction is not new. It can be experienced in everyday life. Think about how the Earth draws everything toward it with its gravity. Now picture a much grander scale, where colossal structures of the universe exert their gravitational influence on clusters of galaxies. The Great Attractor exemplifies this on a much larger canvas. It showcases the interconnectedness of galactic bodies, illustrating that even at cosmic distances, objects influence one another through gravity. The mystery deepens when we consider the nature of the dark matter that constitutes most of the universe's mass. While ordinary matter forms the stars, planets, and galaxies we see, dark matter remains elusive, invisible, yet essential in shaping the cosmos. It is thought that a significant portion of the Great Attractor's mass is comprised of this unseen material, contributing to its powerful gravitational influence. Researchers continue to explore the surrounding region to glean insights into the Great Attractor's composition and structure. They employ an array of advanced technologies, such as radio telescopes and infrared observations, to pierce through the cosmic dust. By mapping the distribution of galaxies in Laniakea and assessing movements, scientists hope to build a clearer picture of this enigmatic gravitational anomaly. One might wonder how this gravitational pull affects us. While it is true that we are being drawn toward the Great Attractor, this process occurs over immense timescales. The motion of galaxies is often measured in millions of years. So, while our trajectory may be set, the journey is slow and imperceptible in human terms. The intricate dance of galaxies is akin to a cosmic ballet, with performers moving gracefully across the stage of the universe. As we continue to study the Great Attractor and its role within the cosmos, it reminds us of the vastness and complexity of the universe. This gravitational anomaly is a testament to the forces at play in our universe, illustrating that there is still so much left for us to discover. Each observation, each measurement, adds to our understanding. But significantly, it also deepens the mystery. In contemplating the Great Attractor, we encounter a marvelous intersection where gravity, galactic evolution, and the mysteries of dark matter converge. This collision of ideas exemplifies our ongoing quest for knowledge, sharing stories of distant worlds that shape our own existence. As we look back on the history of the universe, the Great Attractor serves as a reminder of how little we know and yet how incredibly connected we are. With each new discovery, we peel back another layer of the cosmos, revealing the intricate patterns woven through space and time. The Great Attractor is more than just a point in the sky. It is a bridge to understanding the universe's secrets, urging us to look beyond the stars that light our night sky and into the heart of gravitational wonders that bind us all. The journey continues as we seek to unlock the mysteries of the universe. forever fascinated by the gravitational pull of the Great Attractor and the stories it holds. Quasars, short for quasi-stellar objects, represent one of the most captivating phenomena in our universe. These luminous entities are found at the centers of distant galaxies and are fueled by supermassive black holes, which can contain millions to billions of times the mass of our Sun. Although they are incredibly far away, quasars can outshine entire galaxies, making them some of the brightest objects that we can observe in the cosmos. To understand how they achieve such dazzling brightness, we need to take a closer look at the powerful processes that happen around black holes. At the heart of a quasar lies a supermassive black hole, surrounded by a swirling disk of gas and dust. This disk, known as an accretion disk, forms when material from the surrounding environment falls towards the black hole. As the material spirals inwards, it is heated to extreme temperatures, often reaching millions of degrees Celsius. The intense heat causes this gas to radiate energy across the electromagnetic spectrum, producing immense amounts of light. This process is akin to a cosmic furnace. Imagine a campfire where the wood is turning to ash and glowing warmly. In the case of quasars, the fuel is not wood, but rather gas and dust compressed into a spectacular whirlpool. As energy is released, it can be seen as brilliant light from Earth, traveling across vast distances of space to reach our telescope. The brightness of quasars can be astounding. Some can shine with the brightness of over 1,000 trillion suns. This incredible luminosity is primarily due to the efficiency of the energy conversion happening in the accretion disk. A mere fraction of the mass lost to energy yields a staggering output of light and radiation, making quasars not only an important indicator of black hole activity, but also markers of cosmic evolution. Quasars also provide us with valuable information about the early universe. Most quasars are located billions of light years away, meaning we are observing them as they were billions of years ago. This makes them excellent tools for understanding how galaxies and black holes have evolved over time. Their light carries clues about the conditions of the universe when these quasars were active, providing a glimpse into epochs that would otherwise remain hidden from us. Furthermore, the light from quasars allows astronomers to study the interstellar medium and the formation of galaxies. As the light travels through space, it interacts with the gas and dust it encounters. This interaction can reveal the composition and density of matter in the universe, helping to outline how galaxies formed and evolved. The insights gained from quasars contribute to our understanding of the large-scale structure of the cosmos. As we explore these extraordinary objects, we also uncover the diverse environments from which they emerge. The conditions surrounding a quasar can be extreme, with jets of particles being ejected at nearly the speed of light. These jets can extend far beyond the host galaxy, sometimes reaching distances of millions of light years. The interaction of these jets with the surrounding medium can lead to a variety of phenomena, including radio emissions and the formation of enormous lobes and structures in the cosmos. Each quasar tells a story. Some form in isolation, while others reside in active galaxies bustling with star formation and other activity. Studies have shown that the growth of supermassive black holes is intricately linked to the formation of stars in their host galaxies, presenting a complex relationship between the two. The study of quasars is also a journey through time. Because they are located so far away, their light takes billions of years to reach us. This means that observing a quasar allows us to look back in time and witness the universe in different phases of its evolution. Through this lens, Scientists can piece together how the universe changed and developed over vast stretches of time. Quasars have inspired countless people to look up and wonder about the vastness of the universe. Their brilliance captures the imagination, offering a glimpse into the extreme conditions that can exist in the cosmos. As we learn more about these fascinating beacons of light, we continue to uncover the mysteries of the universe, one quasar at a time. In the ever-expanding realm of astrophysics, quasars remind us of the power and mystery that lie in the depths of space. They alert us to the forces at play in the universe, giving us perspective on our place within it. The dazzling light of quasars not only illuminates our night sky, but also serves as a guide for our quest to understand the history and the fate of the cosmos. As we observe these celestial wonders, we are reminded that with each flicker of light that reaches us, there is a wealth of knowledge waiting to be unlocked about the events that shaped our universe. The ongoing research into quasars will undoubtedly continue to transform our understanding of the cosmos, revealing secrets hidden in their brilliant glow and the dance of forces around their supermassive black holes. The Oort Cloud, a term that may sound intriguing, refers to a distant and mysterious region of our solar system. Imagine a vast expanse of space, far beyond the orbit of the most distant planet, Neptune. This is where the Oort Cloud is believed to exist, though it remains largely unobserved and largely a product of scientific theory. To envision the Oort Cloud, think about the shape of a giant spherical shell surrounding the solar system. It is thought to be composed mainly of icy objects, which are remnants from the early solar system. These objects, often referred to as cometary nuclei, are made of frozen material such as water, ammonia, methane, and other volatile compounds. Picture these icy bodies floating through a dark, cold realm, far from the warm embrace of the sun. One fascinating aspect of the Oort Cloud is its immense size. Scientists estimate that it lies anywhere from about 2,000 to 100,000 astronomical units away from the sun. An astronomical unit is the average distance from the Earth to the sun, roughly 93 million miles. To put this into perspective, if you were to travel to the Oort Cloud, it would take thousands of years at our current space travel speeds. It symbolizes just how expansive our solar system is. So, what role does the Oort Cloud play in the cosmic drama of space? The Oort Cloud is thought to be the origin of long-period comets. Long-period comets are those that take more than 200 years to complete one orbit around the sun. When these icy bodies venture into the inner solar system, they can be illuminated by the sun's light, transforming them into stunning celestial spectacles that capture our imagination. These comets can be seen streaking across the night sky, with their glowing tails trailing behind them like ethereal brushstrokes against the darkness. Scientists believe that disturbances, such as the gravitational influence of nearby stars or molecular clouds passing through our solar system, can nudge these icy objects out of their distant orbits in the Oort Cloud. Once they are dislodged, some of them embark on journeys that bring them close to the sun. During these celestial excursions, they can appear bright and beautiful, sometimes becoming visible from Earth. Imagine witnessing a night sky transformed by a brilliant comet, its body illuminated, and its tail shining like a beacon, capturing the wonder of all who gaze upon it. Notably, there are two distinct parts to the Oort Cloud that scientists refer to: the inner Oort Cloud and the outer Oort Cloud. The inner region is theorized to be closer to the sun and consists of objects that are somewhat more densely packed, while the outer region extends into the vast reaches of our galaxy, where the objects are more spread out and isolated. It's a remarkable reminder of how different the conditions can be within our solar system. The existence of the Oort Cloud, while not directly observable, was proposed due to the behavior of long-period comets. Observations of these comets indicate that they often come from a source deep in the solar system. So scientists started piecing together the possibility of a distant region, leading to the hypothesis of the Oort Cloud. Although we may not visually confirm its presence yet, ongoing research and advances in technology may one day allow us to direct our instruments toward this hidden part of our solar neighborhood. Another captivating aspect of the Oort Cloud is the way it forces us to ponder the enormity of our universe. It symbolizes not just the vastness of the solar system, but also the mysteries that lie beyond our immediate understanding. Scientists continue to study its implications, recognizing that exploring such regions can teach us a great deal about the history of our solar system, the processes that shaped it, and the potential for other celestial bodies forming in similar environments throughout our galaxy. Additionally, the Oort Cloud leads us to consider the possibility of other solar systems harboring similar distant regions filled with icy objects. Just as we gaze into the starry night and ponder our universe, we must also wonder about the myriad other worlds out there. Look up at the sky and let your imagination roam freely. Do other stars have their own Oort Clouds, waiting to release their icy wonders? As our exploration of space continues, the Oort Cloud serves as a reminder of what we have yet to discover. The dreams and aspirations associated with understanding this distant region will likely inspire future generations of astronomers, scientists, and explorers. With each new piece of information we gather, we inch closer to unlocking the secrets that the cosmos holds. The Oort Cloud stands as a testament to nature's artistry and a beacon of the unknown, urging us to look ahead and imagine what lies just beyond our reach. This vast, icy rim around our solar system is both an invitation to someone ready to seize the opportunity to learn about the universe and a gentle nudge to respect the sheer expanse of the unknown waiting amongst the stars. At the very beginning of everything, there existed something we can only describe as a singularity, an endlessly dense and hot point. This singularity contained all the energy and mass of the universe. Then, approximately 13.8 billion years ago, something extraordinary happened. This was an event known as the Big Bang, marking the birth of our universe. Yet, what transpired in the moments following this incredible explosion is what we refer to as the cosmic inflation era. Imagine for a moment a balloon that you are about to inflate. As you begin to blow air into it, the rubber stretches and expands rapidly. This is a simple analogy, but it serves a purpose. In our early universe, something similar occurred, but on a cosmic scale. Within fractions of a second after the Big Bang, the universe expanded exponentially, much faster than the speed of light. This phenomenal growth transformed the very fabric of reality itself. During the inflationary period, the universe swelled to an unimaginable size, exponentially increasing in volume. A region smaller than a proton became larger than a galaxy. To put this in perspective, if the entire observable universe were a basketball, this inflation would mean the initial size was roughly that of a tiny speck of dust. This rapid expansion smoothed out the universe and allowed for the even distribution of matter and energy that we see today. The theory of cosmic inflation was proposed to solve certain puzzles that were apparent in the structure of the universe. For example, if we look at the cosmic microwave background radiation, the afterglow of the Big Bang, we observe that it is remarkably uniform. Yet, there are areas that are slightly different. If the universe had expanded uniformly from the Big Bang without this rapid inflation phase, we wouldn't expect such consistency across vast distances. Inflation provides the explanation for this smoothness and explains how different regions in the universe could have been in contact before their separation. During this period, fluctuations in energy densities occurred. These small variations eventually led to the mass and structure that would form galaxies, stars, and clusters of galaxies. Think of these fluctuations as tiny ripples on the surface of a pond. As the pond begins to settle, those ripples influence the overall formation and shape of the water's surface. Similarly, in the universe, these fluctuations were pivotal in shaping the large-scale structure that exists today. One fascinating aspect of this era is the energy field known as the inflaton field, which is thought to have driven the inflation. This field dominated the energy landscape of the early universe and produced the rapid expansion we are discussing. As it decayed, it released energy, leading to the creation of particles, which eventually formed atoms, stars, and everything else we observe in the cosmos. As we look further into the implications of cosmic inflation, we find it provides a compelling framework for understanding not just the beginnings of our universe, but also its fate. The inflationary model also incorporates ideas about the multiverse, suggesting that what we observe is merely one bubble in a broader cosmic foam. In such a scenario, other universes could have inflated to form their unique structures, each with its own physical laws and constants. What's particularly awe-inspiring is the profound influence cosmic inflation has had on the universe's destiny. It contributed to the smoothness and flatness of space, meaning that as the universe continues to expand, its geometric nature remains consistent with a flat configuration. This concept invites us to ponder the very fabric of space and time. The cosmic inflation era is a portrait of the universe's early days filled with surprises and mysteries. As we study the remnants and patterns left behind from this initial period, we gain insights into the fundamental workings of the universe. Instruments like the Hubble Space Telescope and the Planck satellite have played critical roles in mapping the cosmic microwave background, providing evidence that supports the inflationary theory and helping astronomers paint a clearer picture of our universe's inception. In exploring cosmic inflation, we are exploring not just the history of the universe, but its underlying principle. This grand narrative is filled with excitement and wonder as we realize that the universe has transformed from an infinitesimally small point to an expansive and intricate tapestry of galaxies, stars, and potential life. As we journey through the cosmos, the reflections on the cosmic inflation era remind us of the great interconnectedness of everything. The quest to understand our beginnings is one that humanity has embraced. Each discovery provides another piece of the puzzle, illuminating our place in this vast and majestic universe. Our understanding is always evolving, driven by the same curiosity that led to the realization of cosmic inflation in the first place. A curiosity that inspires future generations to gaze up at the night sky and wonder about the origins and complexity of the universe we inhabit. Hawking radiation is a fascinating concept that sits at the intersection of quantum mechanics and astrophysics. It was first proposed by the renowned physicist Stephen Hawking in 1974. This theoretical prediction offers a glimpse into the incredible and often counterintuitive phenomena that occur in the universe, particularly in the realm of black holes. To understand Hawking radiation, we need to explore the nature of black holes themselves. A black hole is formed when a massive star exhausts its nuclear fuel and collapses under its own gravitational pull. This collapse creates an incredibly dense area in space where gravity is so strong that nothing, not even light, can escape from it. This is why we refer to them as black holes. Now, the concept of Hawking radiation arises from principles of quantum field theory, which suggests that even in a perfect vacuum, many particles and antiparticles consistently pop into and out of existence due to fluctuations in energy. These particles are known as virtual particles. Normally, they annihilate each other almost instantly, leaving no trace behind. However, near the event horizon of a black hole, things get interesting. The event horizon is the boundary surrounding a black hole, beyond which nothing can return once it crosses. Imagine two virtual particles appearing at the event horizon. One of these particles might fall into the black hole, while the other escapes into space. The particle that escapes becomes real, while the one that falls in adds negative energy to the black hole. This process has profound implications. When a particle with negative energy is absorbed by the black hole, it essentially reduces the black hole's mass. Over eons, as this process continues, the black hole could gradually lose mass, leading to a fascinating scenario where it might shrink over time. As the black hole loses energy, it could eventually evaporate completely. This theoretical evaporation raises compelling questions about the fate of black holes and the ultimate fate of matter that falls into them. Hawking radiation extends our understanding of the universe in unexpected ways. It challenges the notion that black holes are eternal and unyielding beasts. Instead, they have the potential for transience, as they can lose their mass through these quantum effects. This idea stands in contrast to classic black hole theory, where the only outcome of falling into a black hole is being crushed in its singularity, a point of infinite density where known laws of physics break down. While Hawking radiation remains a theoretical construct and has not yet been directly observed, its implications are staggering. It also leads us to explore concepts of information loss. According to classical physics, any information that falls into a black hole seems to be lost forever. However, if black holes can emit Hawking radiation and eventually evaporate, what happens to the information contained within them? This dilemma has sparked extensive debate in the scientific community, often referred to as the black hole information paradox. Imagine a universe consisting of numerous black holes emitting Hawking radiation presents a distinctive picture of cosmic evolution. Ideally, if Hawking's proposal holds true, black holes might eventually disappear, leaving behind remnants of the information carried within them. The eventual fate of the universe itself may intertwine with these mysterious entities. To visualize this process, one can picture a cosmic cycle. Black holes forming after massive stars collapse, pull matter into their depths, and over immense stretches of time, they find themselves gradually disappearing, shaping the universe in their wake. This cycle is a reminder of the universe's ever-changing nature and its ability to reorder itself. The study of Hawking radiation also blends into the pursuit of understanding the fundamental building blocks of reality. Researchers are constantly interrogating the nature of space and time, probing deeper into quantum theory and attempting to unify it with general relativity. The quest to reconcile these two pillars of physics is among the most significant challenges in modern science. So, as we gaze into the cosmos, we witness not just the grandeur of stars and galaxies, but also the intricate dance of particles and forces that govern it. In acknowledging the impact of Hawking radiation, we take a step closer to deciphering the universe's most profound mysteries. Each aspect we uncover leaves us with more questions and a deeper appreciation of the complexity and beauty of existence. The universe is not merely a static entity. It is dynamic, alive with the interplay of forces and phenomena that can transform ancient giants, like black holes, into whispers of energy and light that might one day illuminate our understanding of the cosmos. Each discovery propels us further along the path to comprehension, reminding us that even in the shadows of black holes, the universe is rich with surprises waiting to be unveiled. Embracing these ideas allows us to endure the vastness of our existence with curiosity and wonder, echoing the eternal quest for knowledge that defines the human experience. Deep in the heart of cosmology, one of the most profound and intriguing theories about the fate of the universe is encapsulated in what is known as the Big Rip hypothesis. This fascinating concept arises from our understanding of the accelerating expansion of the universe, a phenomenon that has puzzled scientists since its discovery in the late 20th century. While many people are already aware that the universe is expanding, the Big Rip takes this idea to an extreme that challenges our imagination and comprehension of space and time. At the core of the Big Rip hypothesis is the observation that galaxies are moving away from us at ever-increasing speeds. This acceleration is attributed to dark energy, a mysterious force that is believed to comprise approximately 70% of the universe. Dark energy is thought to work against the gravitational forces attempting to pull matter together, resulting in a universe that not only expands, but does so at an accelerating rate. But what if this acceleration continues to amplify, unchecked, over time? Think about this for a moment. As dark energy intensifies, the fabric of the universe could reach a point where it begins to rip apart the structures that define it. Imagine galaxies being torn away from one another so violently that the great cosmic distances we observe today become mere memories of a unified past. Our own Milky Way could face separation from its nearest neighbor, Andromeda, losing its connection with neighboring cosmic entities. As we venture further into the implications of the Big Rip, consider the stars within galaxies. If the expansion continues at an accelerated pace, even the gravitational bonds that hold stars in their orbits around galactic centers may weaken irreparably. Stars may drift away from their galactic homes, untethered and isolated in the vastness of space. The brilliance of the Milky Way, a mosaic of light and energy, could dim as its stars are flung away, each becoming a wanderer in an increasingly empty cosmos. But the story does not end with stars. Delving even deeper, the Big Rip suggests that the consequences could become even more dramatic at the level of atomic structures. Imagine a future where the very atoms that compose all matter begin to be pulled apart. This would represent a catastrophic unraveling of the physical laws as we know them. The bonds between protons, neutrons, and electrons could weaken, leading to a state where even the fundamental building blocks of matter no longer resemble what we understand today. What might this scenario look like? It could lead to a universe that is devoid of galaxies, stars, and planets, floating in an infinite sea of isolated particles. The night sky would transform completely, devoid of the twinkling dots of light that have captivated humanity for millennia. In this future, the cosmos would consist only of a ghostly veil of radiation, an eerie expanse of emptiness. Scientists speculate that this scenario could occur in a time frame vastly beyond human comprehension, roughly 20 billion years from now. To put this into perspective, consider the age of the universe, estimated to be around 13.8 billion years. The Big Rip embraces the notion of a universe constantly in flux, where the rules we apply today evolve and change as dark energy continues its relentless march toward dominion over cosmic forces. The implications of the Big Rip compel us to think about our place in the universe and the transient nature of existence itself. This hypothesis poses provocative questions about time and space, existence and oblivion. Are we merely observers in a grand cosmic show, subject to unfolding events far beyond our control? Perhaps our curiosity about the universe is centered around not only understanding its intricate workings, but also pondering our fate amidst a ceaseless march of cosmic expansion. While the Big Rip remains just one theory among many concerning the ultimate fate of the universe, it serves as a compelling reminder of the mysteries and unpredictability of the cosmos. This theory ignites curiosity, inspiring scientists and thinkers alike to probe deeper into the nature of reality and the unknowns that lie ahead. As we look up at the starry sky, we are compelled to reflect on the complexities of existence, a dance between forces that create and tear apart, illuminate and obscure. Thus, the Big Rip becomes more than just a scientific hypothesis. It embodies the overarching quest for knowledge, the desire to comprehend the enigmatic fabric of our universe. Whether it fills us with dread or wonder, one thing remains certain. The journey of discovery continues, forging paths into the dark, echoing void, where secrets lie yet untold. The story of the universe stretches far beyond any immediate understanding, inviting us to dream, to explore, and to seek meaning in the vast celestial expanse that surrounds us. Imagine standing on Earth and looking up at the night sky. As you gaze at the stars, you are looking into a vast expanse filled with wonders, mysteries, and countless galaxies. But have you ever wondered just how far away those twinkling lights really are? One way to comprehend these enormous distances is through the concept of a light year. A light year is not a measure of time, as its name might suggest, but rather a measure of distance. Specifically, it is the distance that light travels in 1 year. Light travels at an incredible speed of approximately 300,000 kilometers per second, or about 186,000 miles per second. To put that into perspective, light can circle the Earth about 7.5 times in just 1 second. When you multiply this staggering speed by the number of seconds in a year, you arrive at nearly 9.5 trillion kilometers, or about 6 trillion miles. This immense distance can be difficult to grasp. For instance, if you could travel at the speed of light, you could reach the nearest star, Proxima Centauri, in about 4.24 years. That might seem surprising, considering how many stars are visible to the naked eye on a clear night. Each star represents light years of space between us and them. The nearest galaxy, the Andromeda Galaxy, is roughly 2.537 million light years away. These numbers might sound intimidating, but they help to illustrate the vastness of our universe. To further conceptualize a light year, picture this. Imagine a long stretch of road that extends across a landscape. If that road were to represent a light year, driving along it at a typical highway speed of 100 kilometers per hour would mean a journey lasting over 100,000 years to cover that distance. Simply stepping outside and looking at the stars connects us to places that are unimaginably far away, places that have taken light millions of years to reach us. In the world of astronomy, the term light year plays a crucial role. It helps scientists and astronomers communicate distances in a way that is easier to understand. Instead of saying a star is millions or billions of kilometers away, stating it in light years makes it more relatable. It also opens the door to discussions about the universe's size and the incredible variety of celestial objects that inhabit it. Consider the fascinating journey of a beam of light emitted from a distant star. It travels through the cosmos, moving past planets, solar systems, and galaxies, facing obstacles like cosmic dust and gas clouds, all while maintaining that breathtaking speed. When that light finally reaches us, it may have left its origin millions ago, giving us a glimpse into the past, a time when that star shone in its own unique moment. The study of light years also invites us to explore the nature of light itself. Light can be seen in different wavelengths, each carrying information about the universe. For example, visible light lets us see stars, while infrared light reveals hidden stars obscured by dust. Each of these wavelengths provides insights about the objects they come from, helping build a more comprehensive understanding of the cosmos. Light years are also essential when discussing the expansion of the universe. The light we see today, from galaxies that are millions of light years away, tells us not only about their existence, but about their movement and evolution over millions of years. As the universe expands, the light we see becomes redshifted, shifting towards longer wavelengths. This phenomenon opens entrancing conversations about the fate of our universe and the mysteries of dark energy and dark matter. As we stand under the splendid tapestry of the night sky, each star represents a different story and a unique journey, many of which travel across time and space to reach us. The concept of a light year connects us to the broader narrative of the universe, reminding us of our place within this grand celestial arena. So, the next time you find yourself looking up at the stars, consider the distance their light has traveled to reach you. Light years of space filled with countless stories and cosmic wonders waiting to be discovered. The universe is a marvel, and each point of light is a testament to the vast stretches of space that connect us to the universe's history. How incredible it is to look at a star and know that light has traveled eons to grace our eyes. White dwarf stars are one of the fascinating remnants of the stellar life cycle, particularly for those stars that were once low to medium in mass. When a star like our Sun reaches the end of its life, it undergoes a series of transformations that eventually lead to the formation of a white dwarf. These stars offer a glimpse into the final stages of stellar evolution and have unique characteristics that draw the interest of astronomers and scientists alike. To understand white dwarfs, it's essential to start with the life cycle of a star. Stars spend most of their lives in what is called the main sequence phase, where they fuse hydrogen into helium within their core. This process releases a vast amount of energy, which creates the outward pressure that balances the inward gravitational pull. However, once the hydrogen fuel is depleted, stars leave the main sequence and begin to evolve into red giants. In this red giant phase, the core of the star contracts and heats up, allowing helium to fuse into heavier elements like carbon and oxygen. This process continues, and the star may even create elements as heavy as neon and magnesium in its final stages. For low to medium mass stars, after exhausting their fuel, they cannot sustain the pressures needed to fuse heavier elements efficiently. As a result, the outer layers of the star are expelled into space, creating a beautiful planetary nebula. What remains at the heart of this nebula is the white dwarf. Imagine the remnants of a once bright star, now reduced to a dense core, no longer undergoing fusion reactions. These white dwarf stars are incredibly compact, containing a mass similar to that of the Sun, but compressed into a volume comparable to that of Earth. This means they are extremely dense, and a spoonful of white dwarf material would weigh as much as an elephant. The density comes from the gravitational collapse of the star's core, which creates a state known as electron degeneracy pressure. This phenomenon arises due to the principles of quantum mechanics, which state that electrons cannot occupy the same space in the same state. As a white dwarf cools, it gradually dims over time. Initially, these stars can shine brightly due to the residual heat from their formation, but without a source of energy to sustain their brightness, they slowly lose this glow. The cooling process can take billions of years, and it's hypothesized that, eventually, white dwarfs will become cold, dark remnants known as black dwarfs. However, the universe is not old enough for any black dwarfs to exist yet, as the process of cooling takes far longer than the current age of the universe itself. White dwarfs also exhibit interesting characteristics that make them essential for understanding our cosmos. For instance, they can be used as standard candles in astrophysics. By observing the brightness of white dwarfs, scientists can determine their distance from Earth. This is due to the fact that many white dwarfs reach a similar brightness, known as the Chandrasekhar limit, which is about 1.4 solar masses. Beyond this limit, the white dwarf cannot support itself against gravitational collapse, leading to interesting phenomena like type Ia supernovae. If a white dwarf accumulates enough matter from a companion star, it can explode in a spectacular manner, releasing energy equivalent to the luminosity of an entire galaxy for a short period. The study of white dwarf stars also provides insights into the chemical makeup of the universe. As these stars cool and interact with their surroundings, they can exhibit spectral lines from the elements present in their atmospheres. This allows astronomers to analyze the composition of these stars, and by extension, the universe's elements formed through stellar processes. In a cosmic sense, white dwarfs are like the ashes of stars that once burned brightly. They have seen billions of years of cosmic history and represent a quiet, contemplative aspect of the universe. When observing the night sky, some of those faint points of light may very well be distant white dwarfs, quietly transitioning through their cooling phases, holding secrets of the stars that came before. Their existence also raises intriguing questions about the fate of our own solar system. As the sun expands into a red giant and ultimately sheds its outer layers, it will leave behind a white dwarf that will drift through space. This glimpse into our cosmic future reminds us of the cycle of life and death in the universe, where stars are born, live, and ultimately transform into something new. Through the study of white dwarf stars, we gain deeper insights into not only the life cycles of stars, but also the fundamental processes that shape the universe around us. Each white dwarf carries with it a history, a narrative of transformation, and a testament to the beautiful complexity of cosmic evolution. The intricate dance of these stellar remnants continues to inspire fascination, reminding us that even in their final stages, stars have stories to tell. As we explore these celestial wonders, we uncover the mysteries of our universe and our place within it, driving our curiosity and need to understand the cosmos. Gamma-ray bursts, often abbreviated as GIARBs, are among the most captivating phenomena in the cosmos, and they exemplify the universe's dramatic and powerful nature. Imagine an explosion so immense that it can outshine entire galaxies. That is what a gamma-ray burst can do, releasing more energy in a matter of seconds than our sun will emit over its entire lifespan of around 10 billion years. These bursts are typically classified into two categories based on their duration, short and long. Long gamma-ray bursts generally last more than 2 seconds, often linked to the catastrophic events surrounding massive stars. When a massive star exhausts its nuclear fuel, it can no longer support itself against gravitational collapse. The core implodes, creating a black hole, while the outer layers of the star are expelled into space at astonishing speeds. This collapse is accompanied by the powerful jets of gamma rays shooting out from the poles of the newly formed black hole. On the other hand, short gamma-ray bursts, which last less than 2 seconds, are believed to result from the collision of two compact objects, such as neutron stars. As these dense remnants of previous stellar explosions collide, they create shock waves and intense gravitational waves. The result of such a collision could send particles racing outward at nearly the speed of light, producing gamma rays that travel across the universe. The energy released during these bursts is staggering. For perspective, a single gamma ray burst can emit more energy in just a few seconds than the sun will emit throughout its entire existence. This has made GRBs not only subjects of fascination for scientists, but also significant markers in cosmic history. When detected, GRBs can serve as cosmic beacons, revealing information about their origins and the environments in which they occur. The first gamma-ray burst was discovered in the late 1960s, when the Vela satellites, designed to detect clandestine nuclear testing, picked up unusual signals in the gamma-ray spectrum. Initially dismissed as potential Earth-based phenomena, further investigation revealed that these signals were originating from deep space. Since then, thousands of gamma-ray bursts have been catalogued, revealing much about our universe. The light produced by a gamma-ray burst can be billions of times more luminous than that of our sun, making them easily detectable across vast cosmic distances. When one of these bursts occurs, it primarily emits gamma rays, which are high-energy electromagnetic waves. These bursts are so intense that they can be detected from billions of light-years away, offering glimpses into the early universe's most violent events. Gamma-ray bursts can vary tremendously in their afterglow, which can be observed across the electromagnetic spectrum, including visible light, X-rays, and radio waves. As the initial burst fades, this afterglow can linger for hours, days, and in some instances, even weeks, providing astronomers with opportunities to study the aftermath of these incredible explosions. Observing the afterglow helps scientists understand the dynamics of the explosion, the environment from which it originated, and the materials being ejected into space. Moreover, these powerful blasts play a role in the life cycle of galaxies. Some theorize that gamma-ray bursts could have lethal consequences for nearby star systems, potentially sterilizing them by destroying the ozone layer and increasing radiation levels. This suggests that GRBs might play a role in shaping the evolution of life across the universe. Despite their intensity and vast energies, gamma-ray bursts occur relatively infrequently on a cosmic scale. Statistically, they happen roughly once per day, somewhere in the universe. However, because they are so distant, only a few dozen are detected each year. Each detection adds to our understanding of high-energy astrophysics and the underlying mechanisms that drive these colossal explosions. Ultimately, gamma-ray bursts intrigue astronomers, not only because of their energetic nature, but also due to the questions they raise about the universe's formation and growth. They represent the extreme conditions of cosmic events and challenge our understanding of physics, especially in the realms of relativity and gravity. As we continue to explore the universe, advancements in technology promise to yield even more insights into gamma-ray bursts. Future observatories, equipped with sensitive instruments capable of capturing the full spectrum of electromagnetic radiation, will enable scientists to probe deeper into these enigmatic phenomena. Not only will we learn more about GRBs, but we may also glean insights about the environments in which they occur and their impacts on the surrounding cosmos. Participation in these cosmic investigations exemplifies humanity's quest to understand the universe. From the grandeur of stellar explosions to the life cycles of galaxies, the study of gamma-ray bursts reflects a vibrant intersection of science and curiosity. Such inquiries remind us of our place in the universe and the spectacular forces at play in the cosmos, which continually shape the very fabric of our existence. Gamma-ray bursts, with their striking luminosity and energetics, comprise a phenomenal chapter in the ongoing story of the universe, compelling us to look up and wonder about the vastness and mystery that surrounds us. The universe is a vast expanse, a canvas of stars, galaxies, and celestial wonders. Yet between these luminous bodies lies a region that often goes unnoticed, but plays a crucial role in the fabric of our cosmos: the interstellar medium. This term describes the matter that exists in the space between stars within galaxies. It is composed of gas, dust, and cosmic rays, each element contributing to the dynamic processes that shape the universe. When we look into the night sky, we see the sparkling stars, but the space surrounding them is not empty. Rather, it is filled with a mix of hydrogen and helium gas, with trace amounts of other elements like carbon, nitrogen, oxygen, and heavier elements formed in the cores of stars. This interstellar gas is primarily hydrogen, making up about 70% of the entire composition. The presence of these gases is vital, as they serve as the building blocks for new stars. Imagine a vast ocean of hydrogen atoms gently drifting in the cosmic void. In regions where this gas is dense, it can begin to coalesce under the force of gravity. As these clouds of gas come together, they form what are known as molecular clouds. These clouds are incredibly cold, often just a few degrees above absolute zero, and dense enough for star formation to occur. Within these clouds, tiny particles of dust assist in the cooling process, allowing hydrogen molecules to stick together more easily, creating the conditions necessary for stars to ignite. Dust, an often overlooked component of the interstellar medium, is crucial in this cosmic dance. These tiny particles, made of elements such as carbon, silicates, and ice, have a significant impact on the way light travels through space. They can absorb and scatter light, affecting the color and brightness of stars that we observe. Dust also plays a role in the chemical processes that lead to the formation of complex molecules. It acts as a catalyst, enhancing reactions that produce the organic compounds essential for life as we know it. In addition to gas and dust, the interstellar medium is also home to cosmic rays. These high-energy particles are primarily protons, along with heavier ions and electrons, that travel through space at nearly the speed of light. They originate from various sources, including supernovae, active galactic nuclei, and even our solar system. Cosmic rays interact with interstellar gas and dust, contributing to the ionization of gas and influencing the chemical reactions within molecular clouds. Every day, our planet is bombarded by these elusive cosmic rays. Though they are nearly invisible, their effects can be profound. For instance, they contribute to the ionization of atoms in the atmosphere, influencing cloud formation and possibly the Earth's climate over long periods. Understanding how cosmic rays interact with the interstellar medium is crucial for astronomers as they seek to unravel the mysteries of the universe. The interplay between gas, dust, and cosmic rays makes the interstellar medium a dynamic and ever-changing environment. Shocks from supernova explosions or stellar winds from nearby stars can compress the gas, triggering new rounds of star formation. The cycle of birth and rebirth continues as new stars are born, live their lives, and eventually die, dispersing their elements back into the interstellar medium, enriching it further and continuing the cycle of stellar evolution. Moreover, the interstellar medium is not uniform. It consists of several different phases, each characterized by its temperature, density, and composition. These phases can range from cold, dense molecular clouds to warm, neutral hydrogen regions, and even ionized regions filled with hot gas. The transition between these phases is an area of active research in astrophysics, revealing insights about the processes that govern star creation. Understanding the interstellar medium connects to a broader understanding of the universe itself. Cosmic evolution depends on the interplay of matter and energy in these regions. The elements formed in the cores of stars are recycled back into the interstellar medium, contributing to the next generation of stars and potentially planets. This continuous flow of matter is fundamental to the formation of galaxies and the overall structure of the cosmos. As we delve deeper into the mysteries of the cosmos, the study of the interstellar medium provides a glimpse into the birthplaces of stars and the fundamental processes that govern our universe. By observing this vast medium with powerful telescopes, astronomers can infer the history of star formation in galaxies, trace the paths of molecular clouds, and even detect the signatures of exotic chemistry that might hint at the existence of life elsewhere in the universe. So the next time you gaze up at the stars, remember that the space between them is not empty. It is a vital and dynamic tapestry filled with gas, dust, and cosmic rays, woven together to create and sustain the stars that light up our night sky. This quiet, intricate dance of matter and energy is what makes our universe such a rich and fascinating realm to explore, encouraging us to look beyond the stars and wonder at the beautiful complexity of existence. Deep within the universe's vast expanse, stars are born, live, and eventually fade away. Among them, the life cycle of red giant stars presents a remarkable and dramatic transformation, particularly during a phase known as the Helium flash event. This cosmic phenomenon marks a pivotal moment in the evolution of massive stars, where profound changes take place in their cores. To understand the Helium flash event, we must first explore what a red giant star is. As a star like our Sun exhausts its hydrogen fuel in the core, it transitions into the red giant phase. During this stage, the outer layers expand outward, and the core contracts and heats up. This dramatic change is a result of the stellar interior trying to maintain equilibrium against the immense force of gravity. As the core contracts, temperatures soar, reaching levels that can ignite further nuclear reactions. Once the core temperature of a red giant reaches approximately 100 million Kelvin, helium, the byproduct of hydrogen fusion, becomes the star's next target for fusion. The conditions become ripe for helium nuclei, which are positively charged and repel each other, to fuse. However, this fusion does not occur gradually. Instead, it manifests in an explosive manner, hence the term helium flash. Imagine the moment when this fusion starts. The helium nuclei, or alpha particles, begin to collide with enough energy to overcome their natural repulsion, merging into heavier elements like carbon and oxygen. This process is incredibly quick, occurring in just a few moments. In fact, the helium flash is so sudden and intense that it can increase the luminosity of the star significantly, sometimes by thousands of times more than before. During the helium flash, a red giant releases an immense amount of energy. This energy bursts forth in the form of radiation, leading to a temporary brightening of the star. For observers, it might appear as though the star has intensified in brightness drastically within mere moments, a breathtaking sight across the cosmos. Estimates suggest that this phase can produce an energy output equivalent to that of 100,000 suns, packed into a few minutes. Once the helium flash has occurred, the star settles into a more stable fusion process, known as helium burning. In this phase, helium is converted steadily into carbon and oxygen over a longer period, allowing the star to experience a more stable existence before further transformation occurs. The helium flash does not lead directly to the demise of the star, but instead it propels it toward the next stages of its life cycle, including the eventual fusion of heavier elements. This stellar phenomenon also plays a crucial role in the chemical enrichment of the universe. The materials produced by these red giant stars can be dispersed into space when the stars reach the end of their lives, contributing to the formation of new stars, planets, and potentially life itself. Elements like carbon, which are produced during the helium flash, are vital in the formation of organic compounds and biological systems. Interestingly, the helium flash event is not unique to all red giants. In fact, it primarily occurs in stars that possess a certain mass range, typically those that are 1 to 8 times the mass of the Sun. This means that the giants we see in the night sky are engaged in various stages of this complex life cycle, some experiencing the flash, while others may undergo different fusion processes based on their mass and evolution. This journey through the stellar life cycle reminds us that the cosmos is a dynamic tapestry of creation and destruction, where each explosion of fusion sends ripples throughout the universe. The helium flash event can be seen as nature's way of forging new materials in the heart of red giants, intricately linking stellar life and the evolution of galaxies. The helium flash is not only a captivating astronomical event, it also serves as a reminder of the intricate balance of forces at play in the universe. It showcases how such violent and energetic changes can lead to the birth of new stars and planets, emphasizing the continuous cycle of life and death that characterizes the cosmos. As we ponder the helium flash and its implications, it becomes clear that the universe is filled with extraordinary processes that shape our reality. Every star, every burst of fusion, and every element formed contributes to the rich and intricate narrative of astronomical evolution, reminding us of our own origin within the stellar narrative woven throughout time and space. So, the next time you gaze at the night sky, consider the luminous giants burning brightly above, whether they are in the throes of their mighty helium flash or embarking on another chapter of their stellar existence. The cosmos is truly a stage full of wonder and surprises, waiting to be explored. The universe is a vast and wondrous place, teeming with mysteries and wonders that stretch far beyond our comprehension. At the heart of our understanding of this cosmos lies a remarkable figure, approximately 13.8 billion years. This number represents the age of the universe, a timeline that begins with an event known as the Big Bang. Imagine a moment when the universe was not as we know it, but a singular point, infinitely small and infinitely dense. This point housed all the energy that would eventually give birth to everything we see around us today. Galaxies, stars, planets, and even the very atoms that make up our bodies. Then, in an instant, around 13.8 billion years ago, this singularity exploded in a magnificent expansion, cascading space and time into existence. This cataclysmic event marked the beginning of a tremendous journey through time and space. As the universe expanded, it cooled, allowing matter to begin forming. Over the course of millions of years, hydrogen and helium atoms began to coalesce due to gravitational forces, creating clouds of gas known as nebulae. Over time, these clouds would collapse under their own gravity, forming the first stars. Picture the skies of the early universe, filled with the light of newly ignited stars, illuminating the darkness, much like the first flickers of a candle in a room. The formation of these stars brought about the creation of heavier elements through nuclear fusion, elements like carbon and oxygen, which are vital for life as we know it. The stars burned brightly, but their lives were not infinite. Some eventually reached the end of their life cycles, exploding in spectacular supernovae. These explosive deaths scattered elements into space, enriching the cosmic matter around them. This material formed new stars, planets, and eventually, the building blocks of life. Our own sun, for instance, is the product of this cosmic recycling process, formed after several waves of star births and deaths. While the universe was busy creating stars, galaxies began to form as well. Galaxies are massive structures containing billions of stars, gas, dust, and dark matter. The Milky Way, the galaxy that houses our solar system, is about 13.6 billion years old, a mere 200 million years after the universe itself came into being. If you could travel beyond our little corner of the universe, you would find an infinite tapestry of galaxies, each with unique characteristics, shapes, and histories. Some spiral gracefully, while others are elliptical or irregular, each narrating the story of a cosmic dance that has been ongoing for billions of years. As galaxies collided and merged, the universe became increasingly intricate. Within these galaxies, systems of stars formed, including ours. The solar system, with its 8 planets, one of which is home to us, formed about 4.6 billion years ago. This was just a fraction of the universe's timeline, a moment in the grand scheme of cosmic history. After billions of years of evolution, intelligent life emerged on our planet. Humans, curious beings who gaze at the stars and ponder their place in the universe. The Milky Way is just one of an estimated 2 trillion galaxies in the observable universe, which means that our home is but a tiny speck within an enormous cosmic ocean. As we continue to explore and learn, each discovery paints a more detailed picture of our universe's history, revealing the intricate threads that weave together the fabric of existence. But how do scientists measure this age of the universe? The process involves understanding the expansion of space itself. Edwin Hubble, in the early 20th century, discovered that galaxies are moving away from us, suggesting that the universe is expanding. By measuring the rate of this expansion, known as the Hubble constant, astronomers can extrapolate backward to estimate when the Big Bang occurred. This scientific endeavor involves intricate calculations, observations of distant galaxies, and the study of cosmic microwave background radiation, the remnant heat from the Big Bang itself, still detectable today. Every day, researchers push the boundaries of knowledge further, seeking ways to explore the universe's beginnings and its potential futures. Techniques involving sophisticated telescopes and elaborate space missions allow us to capture glimpses of distant galaxies and cosmic phenomena that occurred billions of years ago. In many ways, the universe is a time machine. When we observe distant objects, we look back in time, witnessing celestial events that shaped the cosmos eons before our eyes could even contemplate their existence. The revelation of the universe's age, 13.8 billion years, is a humbling reminder of our shared cosmic heritage. We are part of a story that dates back to the dawn of time, intricately linked to the stars and planets that surround us. As we reflect on this monumental timeline, we are encouraged to look to the stars, curious about what lies beyond and eager to uncover the secrets they may hold. In our vast and beautiful universe, each moment is a continuing chapter, one waiting to be explored and understood. Let this understanding inspire awe and respect for the grand cosmic dance, one that has unfolded for billions of years and continues to invite us into its depths. The universe, in its vastness, presents a grand tapestry known as the cosmic web. This intricate structure serves as the blueprint of the cosmos, connecting galaxies in a magnificent network that spans the cosmos. Imagine a gigantic spider's web, where each strand represents the gravitational pull of matter, intertwining to create a sprawling architecture of filaments and voids. At the heart of this cosmic phenomenon lies the idea that the universe is not uniformly distributed. Instead, matter is woven together into a complex web of galaxies, clusters, and superclusters, separated by vast regions of emptiness, known as voids. These voids can stretch for hundreds of millions of light years, serving as the hauntingly empty spaces in this otherwise bustling cosmic city. The filaments of the cosmic web are where galaxies come to life. These filaments are composed mainly of dark matter, an invisible substance that holds galaxies together and influences their movement. Think of dark matter as the scaffolding that supports the universe's construction. Photons and particles slip through its grasp, but their influence is crucial. Throughout these filaments, galaxies cluster together, perched on the edges of cosmic highways that dictate their journeys through space. When we look at a map of the cosmos, it becomes even clearer how these filaments intertwine. They form a pattern resembling the veins of a leaf or the branches of an intricate tree. Galaxies are not evenly spaced. Instead, they thrive in regions where the density of matter is higher. These areas become bustling hubs of activity, where galaxies can interact, merge, and evolve over billions of years. This ceaseless dance creates a dynamic environment, fostering the birth of new stars and solar systems. Among these clusters and filaments, a phenomenon known as gravitational lensing occurs. This effect, caused by the warping of space-time by massive objects, allows us to peek into the very structure of the cosmic web. Light from distant background galaxies gets bent around a foreground galaxy or cluster, creating distorted images that reveal the presence of dark matter. Observing these warped images not only helps astronomers map the distribution of dark matter, but also gives insights into the history and expansion of the universe. The sizes and shapes of these filaments are truly astounding. Some can stretch across hundreds of millions of light years, connecting dozens of galaxy clusters. Imagine a string connecting beads. The beads represent galaxies, while the string represents the filaments of dark matter and cosmic material, stretching and bending through the vast darkness. These structures find their origins in the very early universe, when tiny fluctuations in density evolved into the grand arrangement we observe today. But what about the voids? These immense spaces, where matter is sparse, are crucial in shaping the universe's overall structure. They are not merely empty, they serve as a counterbalance to the dense region. In fact, their existence influences the movement of galaxies within the cosmic web significantly. They allow galaxies to maintain their paths without colliding, navigating through the universe with a certain grace. The voids can host unique phenomena as well, like cosmic filaments stretching at their edges, where matter begins to gather and pull together, hinting at the ongoing dance of creation and destruction. Not only do these structures influence motion and formation, but they also play a pivotal role in the life cycle of the universe itself. The interplay of filaments and voids contributes to ideas about cosmic evolution. Over billions of years, galaxies will merge, be torn apart, and evolve into entirely new structures. The cosmic web is not static. It constantly shifts and morphs as galaxies interact through gravitational forces, creating new filaments and sometimes leaving behind even larger voids. The connection between the cosmic web and the larger story of the universe is a narrative filled with wonder and complexity. Each filament pulsates with the energy of countless stars, while the voids remain like silent guardians, holding the mysteries of creation. It invites us to ponder questions about the nature of existence itself. What lies beyond the last filament? How did these magnificent structures come to be? As we peer into the depths of the cosmic web with our telescopes, we are truly witnessing the universe's dynamic, living organism. We gaze upon a colossal framework that holds the very essence of creation, a cosmic dance that continues as galaxies twirl, merge, and breathe life into new realms within the universe. What we see in the nighttime sky is just a fraction of the majesty that exists beyond, a mere glimpse into a larger story unfolded in the atomic whispers of the cosmos. With each passing moment, as we discover more about this incredible structure, we grow ever more connected to the universe. The cosmic web is not simply a collection of stars and dust. It embodies the complex relationships among the cosmos' various components and offers a lens through which we can appreciate the interconnectedness of everything that exists. This grand cosmic design inspires awe, igniting our imaginations with the infinite possibilities of what lies beyond. Antimatter is one of the most intriguing concepts in physics, captivating the imagination of scientists and enthusiasts alike. To understand its significance, it helps to first grasp what antimatter is. Simply put, antimatter is the counterpart to the matter that makes up everything in our universe. For every particle of matter, there exists an equivalent particle of antimatter, referred to as its antiparticle. For instance, the antiparticle of an electron, which has a negative charge, is called a positron, and it possesses a positive charge. When matter and antimatter meet, they are annihilated in a burst of energy, a phenomenon famously described by Einstein's equation, E=mc². In theory, during the Big Bang, equal amounts of matter and antimatter should have been produced. So, why do we find ourselves in a universe dominated by matter? This imbalance between matter and antimatter is known as baryon asymmetry and remains one of the great unanswered questions in cosmology and particle physics. To put this in context, consider a simple experiment. Imagine placing a small amount of sugar in a cup of tea. Initially, the sugar granules and tea exist separately. However, once stirred, they blend together, and the resulting mixture appears uniform. If we apply this idea to the early moments of our universe, one would expect that matter and antimatter blended seamlessly. But rather than seeing equal amounts, we predominantly observe matter. There are several hypotheses proposed by scientists to explain this intriguing discrepancy. One line of inquiry suggests that even minute discrepancies in the behaviors of matter and antimatter during the early universe might lead to the creation of more matter than antimatter. The notion is that certain fundamental forces could behave slightly differently when acting on matter compared to antimatter, thus tilting the balance towards matter. One fascinating example comes from the study of certain particle interaction. Researchers have observed behaviors in subatomic particles, like kaons and B-mesons, that hint at differences between particles and their antiparticles. Such phenomena are often explored in high-energy particle physics experiments conducted in massive accelerators like the Large Hadron Collider. Here, scientists collide protons at incredibly high speeds, creating conditions reminiscent of the early universe, allowing them to study various outcomes and test the limits of current theories. Another area of research involves the role of neutrinos, the elusive and nearly massless particles created during reactions in stars and other cosmic processes. Recent findings suggest that neutrinos might interact differently with matter than with antimatter. This differentiation could have contributed to an excess of matter over antimatter, further leading to the conditions we observe today. In addition to particle physics, cosmological models investigate the role of the universe's expansion and the potential impact of different cosmic elements. The sheer size and ongoing expansion of the universe affect physical laws and constants that govern particle interactions. Some theories propose that environmental factors during the universe's infancy might have affected how matter and antimatter behaved, creating regions where matter could thrive while antimatter did not. As researchers delve deeper into the study of matter and antimatter, they also explore the implications of these findings. The potential use of antimatter is already a staple in science fiction. For example, in the world of theoretical propulsion, antimatter could serve as a potent energy source for spacecraft. The energy released from matter-antimatter annihilation is incredibly efficient, offering fascinating possibilities for interstellar travel. Practical applications, however, remain distant. Today, antimatter is primarily produced in minuscule quantities for research purposes. Each particle of antimatter is challenging and expensive to create, costing millions of dollars for just a fraction of a gram. Despite its elusiveness, antimatter has already found utility in the field of medicine, particularly in positron emission tomography, or PET scans, which help doctors visualize and diagnose medical conditions. While antimatter remains a subject of fascination, it also serves as a reminder of the mysteries of the universe. The fact that we predominantly observe matter encourages contemplation about the fundamental workings of our cosmos. The question of why matter outweighs antimatter touches on greater themes of existence and the forces that shape reality itself. As research progresses, scientists continue to peel away the layers of this cosmic puzzle. Advanced experiments and discoveries in particle physics, cosmology, and other related fields hold the promise of illuminating this profound imbalance. Will we one day uncover the very reasons behind the inequality of matter and antimatter? The journey to understanding this enigma not only enriches our knowledge of the universe, but also stimulates our imagination about the possibilities that lie ahead in the realms of science and beyond. The more we learn about antimatter, the more we realize that our universe is even more complex and wondrous than we could have ever imagined. The balance of forces, the interplay between particles, and the cosmic tapestry they weave together prompt essential questions about the nature of reality and our place in the universe. The quest to unravel these mysteries is ongoing, guiding the exploration of the cosmos and pushing the boundaries of human understanding ever forward. Rogue planets are fascinating celestial objects that wander the darkness of space, unbound by the gravitational pull of any star. Imagine a solitary traveler, drifting through the vastness of the galaxy, untethered and free from the constraints of a solar system. This is the essence of a rogue planet, an intriguing mystery that ignites the imagination of scientists and astronomy enthusiasts alike. These planets begin their journey within a solar system, where they orbit a star, just like any other planet. However, due to gravitational perturbations, collisions with other celestial bodies, or the gravitational influence of nearby stars, they can become ejected from their original orbits. This dramatic event can occur in various ways. For instance, a close encounter with a massive planet might disrupt its orbit, sending it spiraling away into the dark void of space. Once a rogue planet is ejected, it can travel immense distances, wandering between stars and never settling into a stable orbit around any. Unlike planets that bask in the warmth of their suns, rogue planets exist in a cold and lonely environment, far from the light that fuels life as we know it. They are often described as the vagabonds of the cosmos, constantly moving through an endless expanse of darkness. There is a captivating quality to rogue planets that beckons researchers to explore their potential characteristics. Some scientists speculate that these planets may have atmospheric conditions similar to those of their starbound cousins. While they may lack the light of a nearby sun, internal heat generated from their formation may allow them to maintain a sort of geothermal energy. This warmth could sustain a thin atmosphere, potentially allowing for the existence of clouds, weather patterns, and even the kinds of chemical reactions that lead to life. Interestingly, the exact number of rogue planets in our galaxy is hard to quantify. Estimates suggest that there could be billions of them coasting through space, perhaps even outnumbering the stars in the Milky Way. If we consider the sheer scale of the universe, the possibility of encountering a rogue planet becomes increasingly plausible. Each rogue planet represents an opportunity to learn more about planetary formation and the dynamics of celestial bodies. Rogue planets come in various sizes and composition. Some may be similar to Earth or Mars, potentially supporting similar geologic and atmospheric quality. Others could be gas giants, resembling Jupiter or Saturn, or even icy bodies akin to the moons of the outer planets. Their diversity sparks curiosity about the myriad ways planets can form and survive in the cosmos. While rogue planets exist far from any star, they occasionally come close to other celestial objects, including stars or planetary systems, creating opportunities for fascinating interaction. The gravitational influence of nearby stars can alter their trajectories, sometimes drawing them into new orbits, or even leading to collision. These encounters can redefine the fate of a rogue planet, perhaps even thrusting it into a new solar system where it may take on a stable existence once more. The search for rogue planets has inspired numerous observational missions and studies. Astronomers utilize advanced telescopes and detection methods to identify these elusive objects, looking for signs of their presence in the darkness. By tracking their movements and studying their characteristics, researchers aim to unravel the secrets they hold about planetary and star formation. The more we learn about these enigmatic wanderers, the more we grasp the complex tapestry of our universe. The existence of rogue planets also prompts intriguing questions about the nature of life and habitability beyond our own solar system. Could rogue planets harbor life in some form, perhaps even life that is different from what we understand? The very thought drives scientists to consider the rich possibilities of alien ecosystems thriving in solitude. If rogue planets can maintain some form of warmth and atmosphere, what kinds of organisms could adapt to survive the harsh conditions of deep space? The quest for knowledge continues, prompting a re-examination of astrobiological theories in light of these wandering worlds. As we set our sights on distant stars and contemplate the vast universe, Rogue planets serve as a reminder of the unpredictability and diversity of planetary systems. They inhabit a unique niche in the cosmic landscape, showcasing the dynamic and sometimes chaotic processes that govern celestial bodies. Each rogue planet tells a story of evolution and change, illustrating the evolution of the cosmos through time. In summary, rogue planets are the lonely wanderers of the galaxy, unbound by stars, yet rich with possibilities. They challenge our understanding of planetary life and formation, and spark undeniable curiosity about the universe. Whether they are cold, barren rocks, or hidden havens for life, these enigmatic planets remind us that there is still so much to discover about our cosmic neighbors and the nature of existence itself. As technology advances and our reach into space deepens, who knows what revelations may await as we explore the mysteries of rogue planets and the secrets they hold. In the vast realms of our universe, there exists a colossal structure that stretches across the cosmic tapestry in an intricate way that challenges our imagination. This monumental formation is known as the Cephat-2 Great Wall, one of the largest known superstructures in the cosmos. A magnificent cosmic filament of galaxies. It spans a breathtaking 500 million light-years long. To comprehend the scale of the Cephat-2 Great Wall, consider this: 500 million light-years is not just a distance. It is a journey through the fabric of space and time. Light, traveling at an astonishing speed of about 186,282 miles per second, takes nearly 500 million years to traverse such a distance. Imagine witnessing light that began its voyage when dinosaurs roamed the Earth. This enormity enables scientists and astronomers to piece together the large-scale structure of the universe. The Great Wall acts as a gravitational anchor, influencing the movements and formations of countless galaxies within its vastness. Picture a cosmic spiderweb where filaments interconnect various structures and species of galaxies, each with their own unique characteristics and histories. This grand arrangement contributes significantly to our understanding of the universe's evolution, revealing how matter clumps together under the force of gravity to form intricate patterns. Efforts to study the Cephat-2 Great Wall have unveiled an astounding number of galaxies embedded within it. More than 30,000 galaxies have been cataloged in this colossal structure, each representing a unique collection of stars, systems, and potentially even worlds. Some of these galaxies are strikingly beautiful, exhibiting colors and formations that entice astronomers as they peer into their depth. The Great Wall is not an isolated phenomenon. It is part of a larger network of superclusters and cosmic filaments that weave across the universe, forming a complex structure that is both mesmerizing and perplexing. This interconnected web is what scientists refer to when discussing the large-scale distribution of matter in the cosmos. As researchers delve deeper into the mysteries of the universe, they discover that these structures provide vital clues about the origin and fate of the cosmos. Understanding the Cephat-2 Great Wall goes beyond mere observation. It requires intricate analysis and interpretation. Astronomers utilize powerful telescopes and advanced technology to capture the light from distant galaxies, enabling them to infer the distances, compositions, and motions of these cosmic entities. The data gleaned from observing the Great Wall contributes to our knowledge of dark matter and dark energy, two fundamental components that make up a significant percentage of the universe. The intergalactic distances and the dynamics of the Great Wall challenge our perceptions of space. When looking at the night sky from Earth, we see individual stars and constellations, Yet these are merely tiny fragments of the larger cosmic puzzle. The Great Wall acts as a reminder of the interconnectivity of the universe and the vastness that lies beyond our planetary home. One might wonder how and when such colossal structures formed. Initially, the universe was a hot and dense point, and as it expanded, matter began to coalesce, forming stars and galaxies. Over billions of years, gravitational forces pulled these structures together, leading to the formation of superclusters and ultimately superstructures like the CFAT2 Great Wall. The intricate dance of creation and destruction gives rise to something both beautiful and complex, showcasing the delicate balance of forces at play in our universe. Astrophysicists continue to study the implications of the CFAT2 Great Wall on our understanding of cosmic evolution. It serves as a laboratory for examining the behavior of galaxies and their interactions over immense distances. Exploring such structures enhances our understanding of how galaxies merge, evolve, and how cosmic history has shaped the universe we see today. Visually, imagine gazing at a map of galaxies spread across the night sky, with the CFAT2 Great Wall incandescently illuminated, showcasing the paths of gravitational influence drawn from one galaxy to another. Each twist and turn in its filament reflects the complex interplay of forces that govern cosmic life. In essence, the CFAT2 Great Wall is more than just an astronomical phenomenon. It embodies the quest for knowledge and the pursuit of understanding the grand design of the universe. It suggests that we too are a part of an expansive whole, inviting us to look beyond the immediate and to ponder our place in the vast cosmos. Through the lens of the CFAT2 Great Wall, we can appreciate the symmetry and organization of the universe, showcasing an intricate balance between chaos and order. Each galaxy, star, and dark matter clump is a testament to the forces at work, reminding us that even in the vast emptiness of space, there is a connection and a story waiting to be told. As we continue to explore these cosmic landscapes, we deepen our appreciation of the universe's magnificence and our role within this grand narrative. Primordial black holes are a fascinating concept in the realm of cosmology. To understand them, we must first journey back to the early moments of the universe, just mere fractions of a second after the Big Bang. During that time, the universe was an extremely hot and dense place, filled with high-energy particles and radiation. It was a period of immense chaos and transformation, where the laws of physics, as we know them, would have seemed very different. In those early conditions, it is thought that small fluctuations in density could have led to the formation of primordial black holes. Unlike the black holes we know today, which typically form from the remnants of massive stars, primordial black holes could have formed from the very fabric of space-time itself. Imagine a bubble in a boiling pot of water. It can expand or collapse based on the energy present. In the same way, certain regions of the universe might have experienced enough gravitational pull to collapse in on themselves, creating these tiny black holes. The intriguing aspect of primordial black holes is their potential sizes. They are theorized to vary greatly, from tiny black holes smaller than an atom to larger ones with masses equivalent to that of a large mountain. This vast range opens up numerous possibilities for how they might exist today. If they formed in the early universe, they might have survived intact through billions of years, remaining undetected until modern observational techniques improved. One of the compelling features of primordial black holes is their potential impact on the universe's evolution. Because they could exert gravitational influence even from a distance, they might have played a role in structure formation within the cosmos. The galaxies we observe today could have been shaped, in part, by these ancient entities. Imagine primordial black holes, acting as anchors, pulling surrounding matter towards them, affecting the arrangements of stars, dust, and gas. Scientists speculate that primordial black holes might also contribute to dark matter, an unseen substance that makes up a significant portion of the universe's total mass. Dark matter cannot be observed directly, as it does not emit light or energy. However, its existence can be inferred from its gravitational effects on visible matter. If a portion of dark matter is actually constituted by primordial black holes, it could explain the mysterious dynamics large-scale structures exhibit. Interestingly, researchers are actively looking for signs of primordial black holes, conducting experiments and analyzing cosmic data. One of the main ways to detect them is through their effects on gravitational waves. When two black holes collide, they create ripples in the fabric of space-time that can be detected by observatories like LIGO and Virgo. These experiments yield valuable information, and understanding the nature of the collisions could help confirm whether primordial black holes exist. Another avenue of research examines cosmic rays, which are high-energy particles that travel through space at nearly the speed of light. Some theories propose that primordial black holes could interact with particles in ways that create extreme bursts of energy detectable on Earth. If scientists can trace these cosmic rays back to their origins, it could provide additional evidence supporting the primordial black hole hypothesis. The importance of studying primordial black holes extends beyond just the understanding of black holes themselves. They may shed light on the conditions present during the universe's formative years and help refine our models of cosmic evolution. By piecing together evidence from these ancient remnants, we could begin to unveil the secrets of the universe's infancy. While the existence of primordial black holes remains theoretical, the discussions surrounding them stimulate curiosity and innovation in astrophysics. Researchers continue to devise new ways to explore and test the boundaries of this hypothesis, utilizing advanced technologies and innovative approaches to data analysis. Every discovery takes humanity one step closer to comprehending the cosmos and our place within it. So, as we ponder the mysteries of the universe, let's appreciate the wonders that primordial black holes may hold. These hypothetical entities serve as a reminder that the cosmos is filled with unimaginable possibilities, and that each question leads to new pathways of discovery. Ideas about black holes remind us of the intricacies of the universe, highlighting our quest for knowledge, understanding, and exploration. The exploration of primordial black holes is not just a scientific endeavor. It is a journey into the depths of our existence and the fabric of reality itself. Each theory, each hypothesis brings us closer to unraveling the tapestry of the universe we inhabit. The night sky, filled with stars, holds secrets of our very origins, waiting to be uncovered by our relentless curiosity. In the vast expanse of the universe, an incredible phenomenon occurs that fundamentally shapes our understanding of space and time. This is the concept of redshift, a captivating and intricate result of the expansion of the universe. To grasp the significance of redshift, we first need to appreciate the very nature of galaxies and their immense distances from us. Galaxies are massive collections of stars, gas, dust, and dark matter, bound together by gravity. Each galaxy is a bustling metropolis of celestial activity, with billions of stars illuminating the dark canvas of space. The nearest galaxy to us, the Andromeda Galaxy, is about 2.5 million light-years away, while others are billions of light-years distant, adding to the sense of scale and wonder we experience when pondering the cosmos. Now, imagine looking at the light emitted by these galaxies. When we observe distant galaxies, we find that the light they emit is not static, but is actually being altered by a phenomenon we call redshift. This effect occurs because the universe itself is expanding, stretching the fabric of space in a way that influences how we perceive light from these distant worlds. The light waves originating from these galaxies travel through this expanding space, and as they do, their wavelength stretches or shifts toward the red end of the electromagnetic spectrum. This shift in wavelength is analogous to the sound of a siren moving away from you. As the ambulance drives further away, the pitch of its siren seems to drop, creating what is known as the Doppler effect. Similarly, with light, the wavelengths stretch as the source moves away from us. For a galaxy that is speeding away due to the expansion of the universe, the light we receive is shifted toward longer wavelengths, hence the term redshift. One of the most extraordinary implications of redshift is that it serves as a cosmic indicator of distance and velocity. The more pronounced the redshift, the faster a galaxy is receding from us. This relationship was famously articulated by the astronomer Edwin Hubble in the early 20th century, leading to the groundbreaking realization that the universe is not static, but is actively expanding. Hubble's observations revealed that galaxies are generally moving away from us, and those further away exhibit a greater redshift. This was a revolutionary insight, as it built the foundation for our modern understanding of cosmology and the dynamic nature of the universe. To illustrate this idea, consider a balloon filled with air. If you were to draw dots on the surface of the balloon and then inflate it, you would observe that each dot moves away from every other dot as the balloon expands. Wow! In a similar way, galaxies are like those dots, moving away from each other as the universe continues to grow. This everyday analogy helps visualize the grand scale of cosmic expansion and the motion of galaxies. Redshift not only informs us about the motion of distant galaxies, but also provides a glimpse into the history of the universe itself. By analyzing the redshift of light from various galaxies, astronomers can estimate the rate of expansion, known as the Hubble constant. This information is crucial for understanding the age and overall structure of the universe. Recent discoveries about dark energy, the mysterious force driving the acceleration of this expansion, further deepen our comprehension of cosmic evolution. In addition, redshift has impressive applications in studying the early universe. When we observe light from extremely distant galaxies, we are peering back in time. The light that reaches us has traveled billions of light years, thus bearing witness to the conditions of the universe billions of years ago. This ancient light reveals the origins of galaxies, stars, and the formation of the universe after the Big Bang. The patterns we see in this light support theories about the universe's infancy, such as the formation of cosmic microwave background radiation, which is a remnant of that early epoch. The implications of redshift extend beyond individual galaxies. It also plays a role in understanding the large-scale structure of the universe. By mapping the distribution of galaxies and their redshifts, astronomers can uncover the cosmic web, a vast network of galaxies and galaxy clusters interconnected by filaments of dark matter. This structure highlights how gravity shapes the universe on the grandest scale. As we continue to explore and learn more about redshift and the expanding universe, the mysteries of our cosmic surroundings unfold further. Scientists employ advanced technology and observation techniques, such as powerful telescopes and spectrometers, to capture the light from the farthest reaches of the universe and decode its secrets. This ongoing quest for knowledge not only satisfies human curiosity, but also fosters a deeper appreciation for the intricate and dynamic cosmos we inhabit. Ultimately, the phenomenon of redshift exemplifies the remarkable and ever-expanding tapestry of the universe. As galaxies move away from us and their light shifts toward red wavelengths, we are reminded of the beauty and complexity of the cosmos. This journey into understanding serves as a testament to human ingenuity and the insatiable desire to explore the unknown, pushing the boundaries of our knowledge and revealing the unfathomable wonders of space. Jupiter, the largest planet in our solar system, is known for its striking beauty and fascinating features. One of these remarkable characteristics is its radiation belts, which are significantly more intense than those found around Earth. Understanding these radiation belts can give us insight into the complex environment that surrounds this gas giant. To begin with, let's talk about what radiation belts are. Essentially, these are zones filled with charged particles, including electrons and ions, held in place by a planet's magnetic field. They are created through various processes, including solar wind interactions and cosmic radiation. On Earth, we have the Van Allen radiation belts that serve as a protective shield, capturing these energetic particles and keeping them from reaching the surface. However, Jupiter's magnetic field is much stronger than Earth's, resulting in radiation belts that are far more powerful and complex. Jupiter's magnetic field is approximately 20,000 times stronger than that of Earth. This immense strength allows it to capture and store a stunning amount of charged particles. The primary source of these particles is the solar wind, a continuous stream of charged particles emitted by the sun. When the solar wind reaches Jupiter, it interacts with the planet's magnetic field, creating intense areas of radiation that can extend outward into space. The process is similar to how a magnet attracts metal shavings, creating a concentrated field. In addition to solar wind, Jupiter's own moon, Io, plays a crucial role in the formation of its radiation belts. Io is one of the most geologically active bodies in the solar system, constantly erupting volcanoes and releasing gases into space. These gases, primarily sulfur dioxide, become ionized and contribute to the population of charged particles in the vicinity of the planet. This interaction produces a torus of plasma surrounding Jupiter, which adds to the existing radiation environment and makes it even more hazardous. The radiation environment near Jupiter is not just intense, it is also dynamic. The belts consist of different layers, categorized by the type and energy of the particles they contain. Closer to the planet, you will find high-energy electrons with energies exceeding millions of electron volts, while further out, lower-energy particles are present. This layered structure results in varying radiation levels, meaning that some regions are far more dangerous than others. Because of this extreme radiation, spacecraft that venture to Jupiter must be specially designed to withstand these harsh conditions. For example, the Juno spacecraft, which entered orbit around Jupiter in 2016, is equipped with a unique radiation vault to protect its sensitive instruments. This allows scientists to study the planet's atmosphere and magnetic field while minimizing the risk of damage from radiation exposure. Another fascinating aspect of Jupiter's radiation belts is their impact on the planet's moons. The intense radiation can affect the surfaces and atmospheres of these satellites. For instance, Europa, one of Jupiter's most intriguing moons, has a radiation environment that is particularly hostile due to particles bombardment. This has significant implications for potential future exploration, especially since Europa is believed to harbor a subsurface ocean beneath its icy crust, making it a prime candidate in the search for extraterrestrial life. Interestingly, the study of Jupiter's radiation belts can also provide insights into space weather. Understanding how these belts interact with the solar wind helps scientists learn more about the fundamental processes that govern the behavior of magnetic fields in planetary systems. This knowledge can then be applied not only to our understanding of Jupiter, but also to other celestial bodies, including exoplanets. In summary, Jupiter's radiation belts serve as an incredible example of the forces at play in our solar system. The immense strength of its magnetic field, coupled with the contributions from its inner moons like Io, creates a complex and intense environment that is far greater than what we experience on Earth. As we continue to explore and study Jupiter, we gain valuable insights into both its unique characteristics and the broader mechanics of planetary science. Exploring these radiation belts not only enhances our knowledge of Jupiter, but also deepens our understanding of the universe. The processes at work in the vicinity of this giant planet offer a window into the interactions between magnetic fields, solar winds, and cosmic phenomena. As we look to the future, the ongoing study of Jupiter will undoubtedly yield new discoveries and help us appreciate the complexity and wonder of our solar system. Galactic cannibalism is a fascinating phenomenon in the universe where larger galaxies merge with and absorb smaller ones. This process can be seen as a cosmic ballet, a dance between massive structures that shapes the very fabric of the universe. Imagine two galaxies, each teeming with stars, gas, dust, and dark matter, drawn together by the force of gravity, entwined in a grand cosmic embrace. To visualize galactic cannibalism, picture the Milky Way, a majestic spiral galaxy housing our solar system, embarking on a cosmic journey. As we look out into the cosmos, we find that the Milky Way is not alone. It exists within a larger gravitational framework, engaging in a celestial dialogue with neighboring galaxies. Among these neighbors are smaller companions, like the large and small Magellanic Clouds, which orbit the Milky Way, drawn ever closer by gravity's unyielding grasp. As these galaxies approach each other, they begin to interact gravitationally. This interaction can lead to a spectacular display of tidal forces. Imagine the immense halo of dark matter surrounding each galaxy, rippling and distorting as they approach one another. It is as if invisible hands are gently pulling apart the structures of the galaxies, causing them to stretch and reshape. The stars within them respond to these gravitational tugs, often being pulled from one galaxy and flung into the other, creating a dynamic exchange of material. Over millions of years, as the large galaxy continues its approach, the smaller galaxy gets stretched further. The gravitational forces become increasingly intense, leading to spectacular distortions in its shape. Spirals can begin to unfurl, tails can stream into space, and new structures emerge from the chaos. In this vast canvas of the universe, the smaller galaxy may become a part of its larger neighbor, assimilating into the Milky Way amidst bursts of new star formation. The merging process is often accompanied by an intense surge of activity. Gas clouds ignite as they collide, leading to the birth of countless new stars. Picture millions of stars lighting up in a brilliant display as gas compresses and heats up, forming new stellar nurseries. This can create vibrant star clusters and even trigger the formation of exotic phenomena like supernova. Such events remind us that destruction can often precede creation, a theme resonant throughout the universe. Interestingly, this process is not limited to the Milky Way. It is a common occurrence across the universe. Many galaxies share similar fates, spiraling through the void and eventually merging with one another. For instance, the Andromeda Galaxy, our closest large neighbor, is on a collision course with the Milky Way, set to merge with us in about 4 billion years. The night sky will be transformed as these two titans of the cosmos collide and coalesce, leading to a new, larger galaxy. Galactic cannibalism also plays a significant role in the evolution of galaxies. Over time, Each merger adds to the mass and complexity of a galaxy, influencing its shape, structure, and stellar population. These mergers can lead to the formation of elliptical galaxies, characterized by a smoother and more rounded appearance, quite different from the more chaotic spiral shapes we often see. While the merging of galaxies is an awe-inspiring spectacle, it is also essential for understanding the growth and evolution of the universe itself. Each interaction contributes to the cosmic web, a vast structure of clusters and superclusters that fills the universe and holds galaxies within its gravitational embrace. Through the lens of galactic cannibalism, we gain insights into the life cycle of galaxies, the forces at play, and the evolution of cosmic structures. Exploring this topic invites us to consider the grand scale of the universe and our place within it. We are but tiny observers in this enigmatic expanse, watching as gigantic structures interact in ways that are both beautiful and violent. The night sky holds evidence of past collisions, remnants of galactic mergers, visible as trails of stars and gas, hinting at the cosmic history written in the fabric of space. As we learn about these processes, we can begin to appreciate the interconnectedness of celestial bodies. Each merger, collision, and interaction is part of a larger cosmic narrative that transcends time and space. It connects galaxies spread across billions of light years, drawing them into a magnificent story of creation and destruction that continuously unfolds. The very concept of galactic cannibalism challenges our perspectives on existence and the universe. It urges us to marvel at the complexity and dynamism of cosmic structures, reminding us that everything is in a state of flux. As galaxies consume one another, they weave a tapestry of stellar evolution that captivates the imagination, illustrating the vastness of space and the intricate dance of galaxies. So, the next time you gaze at the night sky, remember that there is an epic story taking place beyond our immediate sight, an ever-changing cosmos where galaxies reach out to one another and reshape their destinies in a grand ballet of cosmic forces. Through the lens of galactic cannibalism, we glimpse the incredible processes that have shaped our universe and continue to do so, each light year reminding us of the beauty and chaos entwined in this celestial dance.